TON 618 isn't just the biggest black hole we've ever seen, if it's a black hole at all. 10 billion years ago, something tore through that region of space, and the proof has been travelling ever since. Its light is reaching Earth right now. So what is TON 618 really? Why does it grow like it's cheating the universe? And what exactly is the thing that's already coming toward us? Look up, and you are not seeing the sky. You're reading a delayed transmission from a younger universe. What arrives tonight is not danger, but evidence, and it does not ask permission to change us. For most of human history, the heavens felt immediate, fixed lights pinned to a familiar dome. But distance is a time machine, and the deepest distances are the oldest arguments. Somewhere beyond the reach of any telescope's resolving power, a compact engine has been writing in radiation for eons, layering heat, motion, and gravity into a signal we can finally decode. It comes to us stretched thin by expansion, sifted through intergalactic gas, and softened into wavelengths our instruments were built to catch. In that light are fingerprints, spectral lines split and smeared by speed, ratios tuned by temperature, and subtle tilts of polarization that remember magnetic fields. In that light are timestamps too, flickers and delays that betray size, structure, and the geometry of an unseen machine. Yet the deeper we look, the less comfortable the bookkeeping becomes. We have growth laws that behave like speed limits, and we have neat histories for how the first structures assembled. And then we meet an object whose inferred scale sits at the far edge of plausibility, so far out that even careful astronomers hesitate before saying the number out loud. This documentary is not a hunt for an alien weapon or a cosmic omen. It is a forensic investigation into how we know what we know, because TON 618 forces a question that sounds simple and turns out to be corrosive. Are we measuring a monster correctly, or are our rules incomplete? To answer that, we will treat the sky like a lab report. We will follow photons backward through expanding space, and watch how redshift turns raw brightness into a record of era and environment. We will see why a quasar can look like a star yet outshine galaxies, and why its brilliance is not the object itself but the matter being torn apart around it. Then we will do the difficult work, measuring what cannot be imaged. We will use the breadth of emission lines as a proxy for orbital speed, and connect that speed to mass through calibrated relations that carry both power and peril. We will confront the uncertainties openly, orientation, winds, absorption, and the quiet ways a spectrum can lie without ever becoming false. From there, the problem becomes historical. If the mass is even close to right, the universe had to assemble an extreme far earlier than our tidy narratives prefer. That tension is the real threat. Not to Earth, but to certainty, because it suggests the early cosmos could feed, merge, and collapse with a ruthlessness our models smooth over. New observatories have begun to crowd the first billion years with candidates that feel unreasonably bright, unreasonably mature, and unreasonably fast. Some will fade under better analysis, and some will survive it. Either way, the distribution's tail matters, because TON 618 lives in that tail, and tails are where hidden mechanisms announce themselves. We will also enter the engine room itself, where plasma becomes a disk, friction becomes light, and magnetic fields can collimate matter into beams that cross intergalactic space. We will talk about limits that are real, and limits that are assumptions, and the narrow loopholes nature might exploit when the universe is young, dense, and impatient. By the end, the phrase "it's coming" will mean something precise. Not a body drifting toward us through ordinary space, but information arriving through time, information with the power to revise our timelines, our formation stories, and our sense of what the early universe was capable of building. And if TON 618 turns out not to be a simple black hole in a simple story, that will not make the universe safer. It will make it stranger, because the worst possibility is not destruction, but discovery. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. We begin with the message in the light itself, then trace TON 618 from its first catalogued hints to the methods used to weigh the unseeable. From there, we confront the growth problem and the new early universe menagerie, until the final twist clarifies what is truly coming. Tonight the sky looks calm, but it is delivering an ancient event in real time. The stars seem fixed and quiet, yet every point of light is motion, an ongoing broadcast crossing a restless universe. We're not waiting for a thing to arrive, we are receiving what already left. 10.4 billion years ago, photons escaped a violent region around a distant engine. They did not travel through a static stage, because space itself has been stretching beneath them. As the universe expanded, those photons lost energy and slid into longer, redder wavelengths. The same packet of light that began as ultraviolet can reach us as infrared, softened by time. Those photons are reaching Earth now, and they carry a record. That is what "it's coming" means here, and the phrase becomes almost literal when you think in signals. Not a physical object moving toward us through space, and not a threat with momentum. It is light, and with it, information, encoded in brightness, colour, polarization, and timing. Every spectrum is a fingerprint. Every emission line is a timestamp. The universe hides its history in transit, and it does so with a kind of cold honesty. When we look up, we look back, because distance is delay, and delay is memory. The sky is a time machine built from geometry and finite light speed. It shows us a younger cosmos that no longer exists, even if its image still hangs above us. In the constellation Cain's Venatici, there is a point of light with a catalogue name, TON 618. It is classified as a quasar, a beacon powered by a supermassive black hole. It is not nearby, not in any human sense of neighbourhood. It is deep time, pinned to an epoch when galaxies were still assembling their identities. A quasar is not the black hole itself, and that distinction matters for everything that follows. The black hole is dark, but the environment around it can be the brightest thing in the universe. Gas falls inward, spiralling like water into a drain, but the drain is gravity and the water is plasma. Friction and magnetic turbulence heat the flow until it radiates across the spectrum. The accretion disk becomes a furnace, and the surrounding region becomes a lighthouse. That glow is not smooth, and it is not simple. Close to the centre, temperatures can climb high enough to produce intense ultraviolet and X-ray emission. Farther out, cooler gas contributes optical and infrared light, creating a layered, multi-wavelength signature. Above and below the disk, magnetic fields can help launch winds and jets, structures that carve the surrounding medium. Even when we cannot resolve the engine directly, we can read its physics in the light. TON 618 is famous because its numbers feel like a mistake, like a typo that survived peer review. Its estimated mass is about 6.6 times 10 to the 10 solar masses. That is tens of billions of suns in one compact gravitational well. Its luminosity is extreme, and its scale is hard to picture without borrowing metaphors from entire solar systems. The event horizon, if you could outline it, would be enormous by any familiar standard. For a non-rotating black hole, the Schwarzschild radius grows in direct proportion to mass, so the boundary inflates with every added solar mass. At TON 618's scale, that radius becomes a vast sphere of no return, large enough to swallow planetary orbits as if they were dust. Yet even that boundary is only the beginning of the story. The gravitational influence shapes a vast environment of orbiting gas, and the gas does not move gently. The disk and broad line region respond to speeds that can approach a fraction of light. Matter close in completes orbits on timescales that can be measured in days or weeks, not millennia. When we see broad emission lines, we are seeing velocity written as width, motion turned into a smear of wavelength. Yet the most unsettling part is not size, it is timing. TON 618 shines from an era when the universe was young, and the cosmic web was still tightening its threads. The light we receive began its journey when cosmic history had barely begun to settle, when heavy elements were rarer and galaxies were more gas-rich. We are looking at a monster that appears early, almost impatiently early. This is where the story turns from awe to discomfort. Black holes can grow by eating, and the verb is crude but accurate in its implications. They can merge with other black holes, stacking mass through violent unions. They can accrete gas steadily, or in bursts, as if the universe occasionally opened a valve. But each pathway has limits that act like speed limits, and those limits are not optional in our simplest models. Accretion is not perfectly efficient at building mass, and the inefficiency is part of the problem. Some infalling matter turns into radiation before it crosses the horizon, because gravitational energy is converted into heat and light. That radiation pushes back on the inflow, especially when the gas is ionized and easily shoved by photons. The brighter the disk, the harder it becomes to keep feeding, and the engine begins to regulate itself. There is a name for that balance, the Eddington limit. It describes the maximum steady luminosity where outward radiation pressure matches inward gravity for ionized gas. Past that, growth should throttle itself, because the light becomes a kind of wind. In plain terms, the black hole's own brilliance can choke its meal. The Eddington limit is not just a number, and it is not merely a warning sign. It implies a characteristic growth timescale, because if you feed at the Eddington rate with typical radiative efficiency, mass increases exponentially but only so fast. Each doubling takes time, and time is the scarce resource in the early universe. When the available window is measured in a few 100 million to a couple billion years, the arithmetic becomes unforgiving. The result is a tension between what we see and what the simplest growth story allows. Even if a black hole accretes near that limit for long periods, time matters more than optimism. The early universe offers only a narrow window, and that window is crowded with other processes. Galaxies must form, gas must cool, angular momentum must be shed, and fuel must reach the center. To reach tens of billions of solar masses so early, the math becomes strained. It starts to look like a rule was bent, or like we misunderstood the rule. So the mystery is not whether TON 618 will physically reach us. It cannot, because the distances are vast and the expansion of space makes the question irrelevant. The real question is what its existence implies about how cosmic monsters form. If the universe built this engine so quickly, then our clean timelines may be missing a mechanism. If TON 618 is real as measured, then something in the early universe built mass faster than our tidy models allow. Either the seed was bigger than expected, perhaps born from an unusually massive collapse, or the feeding was more extreme than expected, sustained beyond what we assume is stable, or the assumptions about limits are incomplete, and the Eddington line is more like a guideline under certain conditions. And if our assumptions are incomplete, the discomfort spreads outward, because black holes do not grow in isolation. It touches how galaxies assembled, since central engines and their hosts evolved together. It touches how quickly structure emerged after the Big Bang, and how efficiently gas turned into stars and into accretion flows. It touches what we think gravity and matter can do under primordial conditions, when densities were higher and environments were chaotic. The title of this documentary is a provocation. TON 618 is not a black hole, is not a literal claim in the simple sense. It is a narrative lens, and it is meant to focus attention on a mismatch. It points at the gap between a label and the mechanism behind it, where comfortable language can conceal unresolved physics. We call it a black hole because that is the closest category we have, and categories are useful until they become cages. But categories can hide problems, especially when a single object stretches the category to its breaking point. When an object breaks the expected growth curve, the category becomes a question. The question becomes a threat to comfortable explanations, because it suggests we may be naming what we do not yet understand. What, exactly, is arriving now from TON 618? It is a coded signal in light, and the code is not metaphorical. Doppler shifts in emission lines reveal velocity and turbulence, because moving gas changes the observed wavelength. Line widths hint at orbital speeds and mass, because faster motion implies stronger gravity. Redshift fixes the era and the distance, because the expansion of space stretches every feature in the spectrum. Spectra are not just colours, and they are not just pretty graphs. They are physics written as patterns, where each peak and dip corresponds to atomic transitions under specific conditions. Hydrogen lines, carbon lines, magnesium lines shift and broaden, and the broadening carries the signature of extreme motion. Some lines arise in dense, fast gas close in, while narrower lines can come from slower regions farther out. Each feature is a constraint on temperature, density, composition and motion near the central engine. We can treat those lines like a message, and the message has structure. Not a warning aimed at us, and not a prophecy written for human eyes. It is evidence of a system operating under extreme conditions, where gravity organizes matter into a luminous machine. It is a snapshot of an early universe that should not have had time, at least not according to the simplest clocks we carry. The sound language of this story begins there, in the idea of translation. A low hum suggests the disk's relentless rotation, steady and indifferent. Higher tones suggest hot gas and violent shocks, where flows collide and heat spikes. The motif is not musical decoration, and it is not meant to sentimentalize the science. It is a reminder that the engine never rests, even when the light has been travelling for 10 billion years. The visual language begins with a simple idea, and it is an idea built for scale. A mouth in space, opening around a bright core with a ring of firelight light that is not fire at all. Not a monster with intent, but a mechanism with appetite, gravity doing what gravity does. The drift is slow, and the scale is indifferent, and the surrounding starfield becomes a thin dusting against the glare. But we will not linger on metaphor, because metaphor can soften what is sharp. We will return to measurement, because measurement is where the discomfort becomes concrete. How do we estimate a black hole mass at such distance, when we cannot see the horizon? How do line widths translate to gravitational potential, and what assumptions sit inside that translation? How do we separate the quasar's glare from its host galaxy, when the lighthouse overwhelms the shore? In practice, the mass estimate is built from indirect but disciplined steps. Astronomers use the widths of broad emission lines as proxies for orbital velocity in the broad line region. They combine that velocity with an estimated size of the emitting region, often inferred from luminosity-based scaling relations. The method is not guesswork, but it is model-dependent, and model dependence is where systematic bias can hide. When the numbers are extreme, every assumption becomes louder. TON 618 did not enter science as a myth. It entered as a data point in surveys, then as a standout in follow-up observations, where its brightness and redshift marked it as unusual. Names like this are built from catalogues and coordinates, not from legend. The drama comes later, when the numbers refuse to behave and the object stops fitting comfortably among its peers. There is history in that process, because quasars themselves were once a kind of shock. In the mid-20th century, astronomers found star-like points with strange spectra, and the redshifts implied enormous distances. The idea that something so small in the sky could be so luminous forced a rethinking of cosmic power sources. The quasar era taught astronomy to accept engines that outshine galaxies, and to accept that gravity can be an energy source. TON 618 inherits that legacy, and then pushes it further. In this chapter, we establish the frame. We are watching a catastrophe that is already over, yet newly arriving, because light makes time portable. The delay makes it feel present, and that feeling is not an illusion. The message is ancient, but the reception is immediate, and our instruments turn it into numbers we can argue with. Now we widen the frame to the era that produced it. 10 billion years ago, galaxies were assembling faster, colliding more often, and feeding central engines with abundant gas. Star formation rates were higher, and the intergalactic medium was being reshaped by radiation and winds. Quasars were more common, and the universe was more violent, not because it was evil, but because it was young. That context matters because TON 618 is not alone, and loneliness would make it easier to dismiss. Other early quasars also look heavy for their age, even if they do not reach this extreme. Each one is a stress test for growth models, a point where the curve is supposed to bend but does not. Together they suggest a missing chapter in cosmic formation, or at least a missing paragraph in our equations. The JWST era sharpened this tension, because it pushed deeper into the early universe with unprecedented sensitivity. By reaching faint infrared light, it revealed galaxies and black hole candidates at surprising times when the universe was only a fraction of its current age. The frontier is no longer whether early structure exists, because it clearly does. The frontier is how it formed so quickly, and what physical pathways were available in those first crowded epochs. TON 618 sits at the extreme end of that frontier, like a boundary marker hammered into deep time. It is a record breaker, and record breakers are useful even when they are inconvenient. They expose where theories fail first because stress reveals weak joints. They force us to ask whether the failure is in the data, in the interpretation, or in the story we keep telling ourselves. So we will follow a path that moves from the sky to the equations. We will trace how TON 618 was identified and characterized, and why its redshift matters for the timeline. We will examine accretion physics, radiative efficiency, and the Eddington limit because those are the standard rails for growth. We will ask what kinds of seeds could start this race, and what environments could keep the fuel flowing. We will also consider uncomfortable alternatives, because comfort is not a scientific criterion. Super Eddington growth episodes that last longer than expected, perhaps aided by geometry that lets radiation escape without halting inflow. dense early environments that funnel gas with unusual efficiency, reducing the usual bottleneck of angular momentum. Rapid mergers in crowded protogalactic regions, where black holes collide and mass jumps rather than climbs. Even the possibility that our mass estimates hide systematic bias, because extreme objects magnify every calibration error. But the twist promised by the title stays in view, and it is more philosophical than sensational. If the simplest black hole story cannot easily produce TON 618, then black hole becomes shorthand for ignorance. The something worse is not a creature, and it is not a supernatural exception. It is a mechanism we do not fully understand, operating inside physics we thought was settled. And mechanisms do not stay isolated, because the universe is an ecosystem of cause and effect. If the early universe could build one TON 618, it could build others, and it could build them repeatedly. It could build them in ways that reshape galaxies, reionize gas, and alter the timeline of cosmic evolution. The implications travel farther than any object, because they change the rules we use everywhere. So the threat is conceptual, not physical, and that is why it lingers. It is the idea that the universe had access to shortcuts, and that our neat constraints are not the whole map. It is the possibility that our growth limits are local rules, not universal ones, valid in some regimes and porous in others. It is the suspicion that the early cosmos was better at making monsters than we are at explaining them, and that our explanations may be the slower evolving species. We end where we began, with a message arriving now. The photons are indifferent, but they are precise, and precision is its own kind of pressure. They carry the spectral fingerprints of a system that should not exist so soon, and they carry them without commentary. They ask one question in many wavelengths, and the question does not fade when we look away. What is TON 618 really? And what does its existence say about the universe that made it? In the next chapter, we follow the trail of discovery and measurement, and we test whether the monster is in the sky or in our models. The message in Chapter 1 arrived as light, but light alone is not an explanation. Chapter 2 asks how astronomy learned to read that message, then learned to trust it. It is a story about method as much as mystery, about turning faint photons into reliable numbers. TON 618 looks like a point, and that is how the story begins in practice. In a wide-field survey image, it does not announce itself with spiral arms or a glowing halo. It sits among ordinary stars as a small, steady spark, almost too modest for what it will become. Early surveys were built to be impartial, and that impartiality mattered. They photographed huge swathes of sky, then returned night after night to add more plates. In that accumulating archive, TON 618 was not a monster, it was a dot with coordinates. In the mid-20th century, radio astronomy started finding bright sources with no obvious match. New antennas mapped the sky at long wavelengths, where dust and gas do not block the view. Some detections were so intense that they demanded an optical counterpart, yet optical plates showed only star-like points. That mismatch created a new kind of suspect, bright in radio yet visually unimpressive. The sky offered a point source that behaved like a galaxy, but refused to look like one. It was as if the radio sky and the optical sky were disagreeing about what reality should be. Radio positions were also imprecise at first, which deepened the puzzle. An early radio map could point to a patch of sky containing many stars, none of them special. Astronomers had to narrow the location, then gamble on which faint dot was the true counterpart. Astronomers built catalogues to keep track of these oddities, because the sky was filling with them. The names were practical, almost bureaucratic, drawn from survey programs and coordinates. There were no gods or monsters in the naming, only a filing system for anomalies. TON 618 entered that world through systematic searches, where objects were flagged by colour and brightness. It was not famous at first, only unusual enough to be recorded. In the language of surveys, it was a candidate, a target for follow-up, a question mark. The early confusion was reasonable, because telescopes could not resolve distant galaxies well. Even nearby galaxies can blur into featureless smudges on photographic plates, especially in poor seeing. A quasar's host is drowned by its own core, leaving a stellar-looking dot. That star-like appearance was not a trick of imagination, it was a limitation of angular resolution. At great distances, a whole galaxy can span less than an arc-second, smaller than the atmosphere's typical blur. The universe can hide a metropolis behind a single pixel. Then spectra changed everything. because spectra turn light into a measurable pattern. A prism or grating spreads the source into lines and bands, like a barcode. What looks like one point becomes a structured signal, and structure is where physics lives. In a spectrograph, the point is fed through a narrow slit, then dispersed into a rainbow. The detector records intensity as a function of wavelength, and tiny peaks rise above the continuum. Those peaks are not decoration. They are atomic transitions stamped into the light. Those lines didn't match familiar stellar fingerprints, and they did not sit at expected wavelengths. They were displaced, as if the atoms were speaking a shifted language. The pattern was recognizable, yet it had slid away from where it should have been. The shift was redshift, and it was the key that unlocked distance. If the same atomic transition appears at longer wavelengths, something stretched the light in transit. The spectrum becomes a ruler, because the atom provides the tick marks. At first, redshift was treated like a Doppler effect, like a siren dropping in pitch as it recedes. That analogy helps, because motion does shift wavelengths in a predictable way. But for quasars, it is incomplete, and the incompleteness matters. For very distant objects, the dominant effect is expanding space, not simple motion through space. The universe grows, and the light's wavelength grows with it. In plain terms, the photon is not losing energy to friction, it is being carried by a stretching stage. Redshift is written as z, a number that measures fractional stretching of wavelength. If z equals 1, the wavelength doubled between emission and detection. A higher z means the light has been stretched more, and it left earlier. That is why quasars were shocking, because their z values implied enormous distances. A star-like dot was suddenly placed billions of light-years away by its own spectrum. The sky had been hiding deep time inside something that looked like a nearby star. Distance in astronomy is never a single ruler, and it is never free of assumptions. Parallax works nearby, standard candles work farther, and redshift works on cosmic scales. Each method leans on a model, and each model earns trust by surviving tests. But redshift ties into a well-tested expansion history, anchored by many observations. The cosmic microwave background, galaxy clustering, and supernova distances all constrain the same curve. When those independent lines of evidence converge, the redshift scale becomes more than a guess. When we say TON 618 is about 10.4 billion light-years away, we are compressing a cosmology calculation. We are translating redshift into a distance measure within a specific universe model. The phrase is simple, but the machinery behind it is careful. That phrase also hides a second meaning, because distance is delay. We are not seeing where it is now, we are seeing what it was then. The telescope is not a window onto the present, it is a recorder playing an old signal. 10.4 billion light-years is not only a separation in space, it is a separation in time. The photons left when the universe was younger, and they carry that youth. They carry the chemical state of the gas, the intensity of the engine, and the conditions of that era. So the correct instinct is to ask two questions at once. How far is it in today's coordinates, and how long has its light been travelling? Those are not the same question, because the universe changed while the light was en route. Look back time answers the second question, and it is the one that matters for origin stories. It tells us how early the engine was already operating at full power. It tells us whether the universe had enough time to build what we think we see. The visual consequence is subtle but important. When we look at TON 618, we're looking across a universe that was denser, more active, and more gas-rich. The space between then and now is not empty history, it is an evolving medium. This is where the investigative tone sharpens, because the numbers are not taken on faith. Every claim about TON 618 rests on what instruments actually measure. The romance of the object is built from the discipline of calibration. The first measurement is position and brightness, recorded across different bands. Photographic plates became digital surveys, and surveys became pipelines that flag anomalies. A modern pipeline does in minutes what once took months of careful inspection. Brightness is not one number, because the sky has many colours. Astronomers measure flux through filters, building a rough spectral energy distribution from discrete points. A quasar's colours can look strange, because emission lines and redshift reshape what each filter captures. The second measurement is the spectrum, which gives redshift and composition clues. Broad emission lines identify fast gas, and narrow lines identify slower regions farther out. The spectrum is also a diagnostic of ionization. because different lines require different energies. In practice, the spectrum is a battlefield of features. The continuum slopes up and down, lines sit on top of it, and absorption can carve into it. The analyst has to decide what is intrinsic, what is intervening material, and what is instrumental artifact. The third measurement is variability, because quasars flicker on human timescales. That flicker is not noise, it is a size constraint, because large regions cannot change quickly. A galaxy of stars averages itself out, but a compact engine can stutter. If brightness changes over days or weeks, the emitting region cannot be light-years wide. Causality limits the size because information cannot travel faster than light. Even if the physics is violent, the signal cannot coordinate across a region larger than the time allows. Together, spectrum and variability build a picture of a compact engine. A galaxy of stars cannot brighten and dim as one unit, but an accretion flow can. The logic is almost ruthless, because it uses the universe's speed limit as a measuring tape. Quasars became recognized as distant, hyperluminous engines because no stellar process could pay the energy bill. Nuclear fusion is efficient, but it cannot reach quasar luminosities in a point source. To match the power, you would need an impossible density of supernova in a tiny volume. Gravity can, because accretion converts mass into radiation with high efficiency. Matter falling deep into a potential well can release more energy per kilogram than fusion. The energy is not created from nothing, it is extracted from the drop in gravitational potential. That is the core idea behind the quasar model, and it explains the lighthouse effect. The black hole is dark, but the infalling gas becomes a furnace. The light is not from the hole itself, it is from matter being shredded, heated, and forced to radiate. A useful image is a cosmic whirlpool, but the physics is more exacting. Gas spirals inward because it can shed angular momentum, often through magnetic turbulence. As it loses that support, it falls deeper, heats up, and radiates away the energy it cannot keep. Quasar anatomy is a layered structure, inferred from light rather than direct images. The central object is a supermassive black hole, setting the gravity and the scale. Its event horizon is tiny compared to the galaxy, yet it controls the innermost dynamics. Around it sits an accretion disk, hot and bright, producing much of the ultraviolet and optical continuum. Magnetic turbulence and friction heat the disk, and the disk radiates. The inner disk can reach temperatures where ultraviolet dominates, while outer regions glow more gently. Above and below the disk, gas clouds move at high speed in the broadline region. Their emission lines are broadened by Doppler motion, turning velocity into width. The broader the line, the faster the gas and the deeper the gravitational well must be. Farther out, a dusty torus absorbs and re-radiates energy in the infrared. Orientation matters, because dust can hide the inner regions, changing what type of quasar we think we see. The same engine can look different depending on whether we peer through the dust or above it. Some quasars also launch relativistic jets, narrow beams powered by magnetic fields near the black hole. Jets are not guaranteed, but when present they dominate radio emission. They can punch through the host galaxy, carrying energy far beyond the central parsec. This framework solved the early confusion because it explained star-like appearance and extreme power together. A compact engine can be brilliant, and a distant host can be invisible. What looked like a star was really a galaxy nucleus turned into an overexposed point. TON 618 sits inside that framework, but it pushes the parameters toward the edge. It is not only distant, it is extraordinarily luminous, and its lines imply extreme velocities. The object does not break the model, but it tests how far the model can be stretched. To understand why, we need to be clear about what the spectrum is telling us. The continuum brightness estimates how much energy is being emitted across wavelengths. The shape of that continuum also hints at temperature gradients, dust reprocessing, and absorption along the line of sight. Emission lines identify elements and ionization states, which reflect temperature and radiation intensity. The presence of strong lines means dense gas is being bathed in hard light. It means photons energetic enough to strip electrons are abundant near the nucleus. Line widths measure velocity dispersion in the emitting gas, often thousands of kilometers per second. In the simplest interpretation, those speeds are orbital, set by central gravity. The gas is not calmly drifting, it is racing in a deep potential well. Astronomers use that idea to estimate black hole mass with virial methods. They combine a velocity from line width with a size scale for the broadline region. The logic is classical. Faster motion at a given radius implies more enclosed mass. The size scale can be measured directly in some quasars through reverberation mapping. A flare in the continuum is echoed later in the lines, and the delay gives a light travel distance. The technique is elegant because it turns time into a ruler. Reverberation mapping also gives a sense of geometry, even when the region is unresolved. Different lines respond with different delays, implying stratified zones of ionization. The nucleus becomes a three-dimensional structure reconstructed from echoes. For very distant quasars, reverberation mapping is difficult, so scaling relations are used. Luminosity correlates with broadline region size based on nearer calibrators. The farther the object, the more we lean on that empirical bridge. That is powerful, but it is also where uncertainty can hide. If an extreme quasar does not follow the same scaling, mass estimates can drift. The method is not fragile, but it is sensitive to assumptions about how typical the extreme really is. So the story is not that TON 618 was discovered as a monster immediately. The story is that it was catalogued, then measured, then reinterpreted as methods improved. Each step tightened the constraints, turning an odd point into a physical challenge. Its catalogue identity reflects the era of survey astronomy, when wide searches found more odd points than any team could study deeply. Follow-up spectroscopy separated ordinary stars from distant engines. The quasar population emerged statistically before it was understood individually. Once the redshift was established, the luminosity became unavoidable. A faint-looking point can be intrinsically blinding if it is far enough away. The eye is easily fooled, because apparent brightness is a mix of power and distance. Luminosity is computed from observed flux and distance, with cosmological corrections. The corrections account for redshifted photons and the stretching of time, which affects how energy arrives. The calculation is not just geometry, it is geometry inside an expanding universe. If distance is huge, the intrinsic power must be huge to deliver the measured flux. This is where the quasar stops being a curiosity and becomes a furnace. The numbers force the conclusion, even if the conclusion feels absurd. That is why quasars are called lighthouses in a young universe. They are visible across cosmic distances because they convert in falling matter into radiation with brutal efficiency. They are also beacons for mapping the early cosmos, because their light cuts through time. But calling them lighthouses can hide the violence, because the beam is not a gentle lamp. The radiation field is intense enough to ionize gas across a galaxy and drive winds. The nucleus can heat, strip, and push its surroundings, reshaping the host's future. In the early universe, that mattered even more because galaxies were gas-rich and chaotic. Feeding the center was easier, and the consequences of feeding were larger. When cold gas is abundant, the nucleus has more fuel, and the feedback has more material to strike. Quasars were more common at earlier epochs, and that is not an accident. The cosmic supply chain was different, with more cold gas and more mergers funneling material inward. The universe was building galaxies rapidly, and the central engines were part of that construction. TON 618's epoch is part of its threat to our certainty, because it is already massive early. The light left when the universe had less time to build such an engine. The question is not only how bright it is, but how quickly such brightness could be assembled. This chapter keeps returning to one discipline, because it is the only way to stay honest. We do not see the black hole, we infer it from how matter behaves around it. The inference is indirect, yet it is grounded in repeatable measurements. We infer it from line widths that imply deep gravity wells. We infer it from rapid variability that implies compact emission regions. We infer it from the continuum shape that matches hot accretion disks and reprocessed dust emission. We infer it from radio properties when jets are present, because jets require extreme conditions near the center. We infer it from the consistency across many quasars, because a single object can mislead. The confidence comes from a population that repeats the same physics. Each inference is strong, but each depends on a model that can be tested and refined. The investigative question is not whether the model works in general, but whether it breaks at extremes. TON 618 lives in the regime where small biases can become large conclusions, so we pause on redshift again, because it is the anchor for every other number. Redshift is measured directly from spectral features, and it is hard to fake consistently. A single line could be misidentified, but a whole pattern shifted together is harder to dismiss. Multiple lines shifted by the same factor point to a real stretching of the entire spectrum. That coherence is why redshift became trusted as a distance indicator. It is also why spectroscopy became the decisive tool for sorting the sky's point-like mysteries. Still, redshift does not hand us a simple mileage number. It hands us a relationship to expansion history. And expansion history is measured by many independent probes. The conversion from Z to distance depends on parameters like the Hubble constant and matter density. When those probes agree, the distance ladder becomes a distance web. TON 6-18's distance is not a single guess. It is a placement within a consistent cosmic map. The map is revised over time, but it does not swing wildly because it is over-constrained. The map then turns distance into time, because the universe has a known age and a known expansion curve. Look-back time tells us when the photons began their journey. It tells us the cosmic chapter in which TON 6-18 was already shining. That is why the phrase 10.4 billion light-years away can mislead. It sounds like a static separation, but it is really a time-stamped signal from an earlier universe. The number is a translation, not a direct measurement with a tape. The object has moved since then, and the space between has expanded. The light travelled through a changing cosmos, and its wavelength records the change. In a sense, the photon is a witness to the universe's growth, carrying the imprint of that expansion. Once distance is set, brightness becomes a physical claim. The observed flux becomes an intrinsic luminosity, and the intrinsic luminosity demands a power source. The universe does not allow arbitrary brightness without paying in mass, energy, or both. Accretion is that power source, and it can outshine entire galaxies because it is concentrated. A galaxy spreads its fusion across billions of stars, but a quasar concentrates energy near one center. Concentration changes everything, because it changes temperature, density, and efficiency. The accretion disk radiates across the spectrum, and the hottest regions peak in ultraviolet and X-rays. Cooler regions and dust re-radiate in optical and infrared, extending the output. The result is a multi-wavelength signature that looks like a system, not a single lamp. The broadline region adds another signature, because it reprocesses the continuum into emission lines. Those lines carry velocity information, and velocity points back to mass. The nucleus cannot hide its gravity, because the gas announces it through motion. So the measurements form a loop that tightens into a conclusion. Redshift sets distance and era, luminosity sets energy scale, and line width set gravitational scale. Each piece supports the others, and the story becomes harder to escape. When TON 6-18 is placed on that loop, the numbers become uncomfortable. A very bright quasar at high redshift implies a very powerful engine early in cosmic history. It implies not only mass, but a growth path that had little time to unfold. The discomfort is not only philosophical, it is quantitative. If luminosity is high, the accretion rate must be high, unless efficiency is exotic. If the accretion rate is high and sustained, the black hole should grow rapidly, but radiation pressure should fight the inflow. That tension is the seed of the next chapter, and it is not a minor technicality. It is the universe's bookkeeping problem written in light. How do you feed a monster while its own brightness tries to blow the food away? Before we weigh anything, we need to be clear about what powered by a black hole means observationally. It means the best model explains the spectrum, variability, and energetics together. It means the model predicts relationships that match what we see across many objects. It means alternative engines fail to match the data without adding more problems. Starbursts cannot produce the compact variability and the extreme line widths at the same time. They can be bright, but their brightness is distributed, and distribution dilutes rapid change. It also means we accept indirect evidence as the normal mode in astronomy. We rarely touch the object, we read its light, and we build a consistent physical story. The story is judged by coherence, by predictive power, and by survival under new data. TON 6-18's story begins in catalogues and surveys, but it becomes a test of that consistency. The object is not a single measurement, it is a convergence of measurements. Its reality is the overlap of independent constraints, each with its own instrument and method. That convergence is why it stayed in the literature and grew in notoriety. It did not vanish with better data, it became sharper as methods improved. The more carefully it was examined, the more it insisted on being extreme. Still, the chapter keeps one caution in frame. because mystery thrives on overconfidence. Extreme luminosity can bias samples, and extreme objects can strain calibrations. The brightest sources are easiest to find, and that ease can distort our sense of what is typical. Dust, orientation, lensing, and line physics can all distort what we infer. A responsible narrative keeps track of those possibilities, even while the main conclusion holds. The goal is not to inflate the monster, but to measure it honestly. Gravitational lensing is one example, because it can amplify brightness without changing intrinsic power. If a foreground mass bends light, a quasar can appear brighter than it is. In strong cases, lensing can split the image, creating multiple points or arcs. So astronomers check for lensing signatures and multiple images, and they compare line properties to typical quasars. TON 618 does not present as an obvious lensed system. Its appearance does not show the clean duplications that often betray strong lensing. Another example is beaming from jets, which can boost observed flux along our line of sight. If a jet points toward us, relativistic effects can brighten the source dramatically. But TON 618's classification and spectral properties do not reduce to a simple blazar-like case. So the working interpretation remains that the luminosity is largely intrinsic, produced by accretion. That interpretation is not a slogan. It is the least broken explanation. It is the model that fits the most data with the fewest special pleadings. Now the anatomy matters again, because each region contributes a clue. The disk sets the continuum, the broadline region sets the velocity widths, and the torus sets infrared reprocessing. Each layer is inferred from a different part of the spectrum, like instruments in an orchestra. If jets exist, they add radio power and sometimes high energy emission. If jets do not dominate, the optical and ultraviolet output still demands a deep gravitational engine. Either way, the nucleus must be compact, because the variability and line widths insist on compactness. Variability ties these regions together, because changes propagate outward. The inner disk can change quickly, and outer regions respond with delays that encode their size. Even when we cannot measure the delays directly, the principle anchors our intuition. Even without direct reverberation mapping for TON 618, the general behavior supports a compact central source. The quasar model is not a guess, it is a framework built from many objects. TON 618 is a rare specimen, but it speaks the same physical language, so the investigative question becomes narrower and more dangerous. If the framework is right, then TON 618 implies an extreme black hole mass and an extreme growth history. The object becomes less a curiosity and more a stress test for cosmic timelines. This is where the story turns from discovery to accounting, because power has a price. The brighter the lighthouse, the heavier the engine must be, or the more efficiently it must feed. Every watt of light implies a certain rate of mass consumption near the horizon. We have now built the chain from survey detection to physical inference. A point source becomes a quasar through spectroscopy, and a quasar becomes a mass estimate through line widths and luminosity. The chain is strong, but it is only as honest as its weakest assumption. We have also built the time axis that makes it unsettling. High redshift means early epoch, and early epoch means less time for growth. The universe is young in that frame, and youth is supposed to limit what can be built, so the chapter ends by tightening the central question rather than answering it. What is TON 618 really, if its inferred mass strains ordinary growth limits? If the numbers are right, then something about early feeding, early seeding, or early physics must be unusually effective. The next step is to weigh the monster with the best tools we have, then interrogate every assumption inside those tools. We move from finding the lighthouse to measuring the engine that powers it. We prepare to ask whether the mass is truly as large as it seems, and what that implies. And we keep the hook from the opening in view, because it is the real reason this matters. 10 billion years ago, something violent happened around this engine, and its evidence is arriving now. The light is not a threat, but it is a confession from the past. Not a warning aimed at Earth, and not a prophecy about our future. It is a message about the universe's past, and about what the early cosmos could build. It asks whether our neat timelines are missing a fast lane. If TON 618 is even close to what it appears to be, then the worst thing coming is not a black hole. It is the implication that our timelines for making monsters are incomplete. The lighthouse does not only illuminate the early universe, it exposes the gaps in our accounting. We have a lighthouse and a timestamp. Now we need a scale. TON 618 is too far to resolve directly, so mass is inferred from consequences rather than from a picture. We measure how gas moves, how light varies, and how brightness pushes back against infalling matter. Each method is indirect, yet each is anchored in gravity, atomic physics, and the finite speed of light. What we're really doing is turning an unresolved point into a physical system with dimensions. The core problem is simple to state and hard to accept, especially when the numbers stop feeling like astronomy. If the central mass is tens of billions of suns, then the early universe built a giant fast. If the mass is smaller, the quasar is still extreme and still demands an explanation. Either way, the measurement becomes a test of how well we understand luminous accretion. Astronomers start with the broad emission lines, because motion writes itself into spectra with ruthless honesty. In a darkened control room, a quasar spectrum looks like a comb of peaks riding on a bright continuum. Gas near the nucleus emits lines from hydrogen, carbon, magnesium, and other ions, and those lines carry a fingerprint of speed. On the screen, the peaks are not just pretty, they are coded kinematics. Those peaks are widened by Doppler shifts from clouds moving at thousands of kilometers per second. Some gas is moving toward us, shifting photons slightly bluer, while other gas is moving away, shifting them redder. Add the contributions together and a thin line becomes a thick one, like a violin note smeared into a roar. The widening is a statistical portrait of many orbits superimposed. A narrow line usually means slow gas, often farther out in the host environment where gravity is weaker. A broad line usually means fast gas, generally closer into the central engine where the potential well steepens. The broadline region is not a single ring, but a thick zone of dense clouds, filaments, and winds. In many models it is layered, with different ions favouring different radii and densities. In that zone, atoms are battered by ultraviolet and X-ray radiation from the inner accretion flow. Electrons are knocked free, then captured again, and each capture can release a photon at a characteristic wavelength. The result is emission lines that are both a chemical inventory and a dynamical record. The line ratios also hint at temperature, density, and ionization state, plain language clues about how harsh the environment is. Line width becomes a velocity scale, often summarized as a characteristic dispersion, or a full width at half maximum. Observers fit the line profile, subtract the underlying continuum, and correct for instrumental broadening. What remains is the astrophysical width, which is the part gravity and gas dynamics are allowed to explain. Even the baseline matters, because a slightly tilted continuum can inflate the wings. The working assumption is virial motion, where gravity dominates the cloud dynamics over long times. In that regime, orbital speed is set mainly by the central mass, not by the cloud's own pressure. The word virial sounds abstract, but it is a bookkeeping rule for bound systems. It connects kinetic energy and gravitational potential energy in a way that survives messy details. The logic is classical and brutal, and it is the same logic that weighs stars in binary systems. Faster orbital motion at a given radius requires more enclosed mass. If we can estimate the velocity and the radius, we can estimate the mass. The challenge is that we do not get to choose the radius, we have to infer it. This is the virial mass estimate, and it is the workhorse for distant quasars where direct imaging is impossible. It uses a formula that looks almost too familiar, like a planetary orbit scaled up to galactic violence. Mass is proportional to velocity squared times radius, with a factor for geometry and orientation. That factor hides the uncomfortable truth that we do not know the exact shape of the emitting region. Velocity comes from the line width, but radius is the harder part because TON 618 is far and compact. We cannot image the broadline region in TON 618 because even the best telescopes see it as a point, so we need a way to turn light into a ruler. In astronomy, time is often the only tape measure that reaches across such distances. Reverberation mapping is the cleanest concept for that ruler, and its beauty is almost embarrassingly simple. The accretion disk continuum varies, because the inner flow flickers, heats, cools, and reorganizes. The broad lines respond after a delay, because the gas is lit by that changing continuum. Visually, it is an echo in light rather than in sound. The delay is not a guess about complicated plasma physics, and it is not a model-dependent parameter. It is light travel time across the system, and light travel time is a distance. If the continuum brightens today and the line brightens 10 days later, the emitting gas is about 10 light days away. That is a geometric statement, even when the structure is invisible. In practice, the signal is extracted by cross-correlating two light curves, one for the continuum and one for the line. The peak in that correlation gives a characteristic lag, and the width of the peak hints at a spread of radii. Even when the data are noisy, the method is grounded in causality. You cannot get an echo before you get the flash. Reverberation mapping turns time into geometry when the source is unresolved, and it does so without needing to see the structure. It also reveals stratification, because different lines respond at different delays as ionization conditions change with radius. High ionization lines tend to respond faster, implying they arise closer in where the radiation field is harsher. Lower ionization lines answer more slowly, as if the system has nested shells. For TON 618, full reverberation mapping is difficult in practice, even though the concept is straightforward. The object is faint in time domain terms, and the timescales are stretched by cosmic time dilation. Monitoring campaigns would need long baselines, stable calibration, and patience measured in years. The data must also be consistent across instruments and seasons, which is harder than it sounds. Time dilation is not a minor footnote, because it slows the observed variability by a factor of 1 plus redshift. A lag that would be weeks in the quasar's rest frame can become months in hours. That stretches observing schedules and makes it harder to separate real echoes from seasonal gaps. It also means the quasar's heartbeat arrives to us in slow motion. So astronomers often use a calibrated shortcut, and the shortcut is built from decades of nearby monitoring. Nearby quasars with reverberation measurements define an empirical relationship between luminosity and broadline region size. Brighter quasars tend to have larger broadline regions, because the ionizing field reaches farther before it becomes too diluted. The scaling is not magic. It is photoionization physics expressed as an observed trend. That relationship is called the radius to luminosity scaling, and it is a bridge across distance and resolution. Measure the continuum luminosity, infer the broadline radius, then combine with the line width. The result is a single epoch mass estimate for a far quasar, derived from one spectrum and careful calibration. It is an accountant's method, but it rests on years of time domain labour. Historically, this approach grew out of a shift in how astronomers treated quasars in the late 20th century. Quasars were once mysterious radio stars, then they became engines powered by accretion onto black holes. Reverberation mapping helped turn that engine from a metaphor into a measurable structure. The move from speculation to measurement is part of the drama here. This is where the story turns from discovery to accounting, because every step carries assumptions that must be paid for. The line must trace gravity rather than a pure outflow, even though winds are common in luminous quasars. The radius scaling must still apply at the extreme luminous end, where the physics may change. At the top of the luminosity ladder, even small deviations can matter. The geometry factor must not be wildly wrong, yet geometry is exactly what we cannot image directly. The broadline region could be spherical, disc-like, or something in between, and each shape projects differently onto our line of sight. Even the distribution of clouds, clumpy or smooth, can tilt the inferred mass. A thick, turbulent structure can broaden lines without changing the central mass. Even with those caveats, the method is not casual or improvised, and it is not a single paper's trick. It is calibrated on many objects, cross-checked with different lines and refined as data improve. It remains the best available tool when direct mapping is out of reach. The credibility comes from repetition across samples, not from one spectacular target. In practice, different emission lines are used as mass proxies depending on redshift and instrument bandpass. H-beta is a traditional anchor at lower redshift, because it is well studied in reverberation samples and sits in accessible optical wavelengths. At higher redshift, Ming2 and C4 become accessible and are used with care. The choice is partly physics and partly what the universe lets our detectors see. Each line is a compromise between observability and purity as a dynamical tracer. Observers must correct for blends, because ion emission can form a pseudo-continuum that hides the true line wings. They also correct for absorption features that can carve away part of a profile and mimic asymmetry. In extreme cases, the spectrum becomes a crowded city of overlapping features. SIEF is powerful but risky, because it can be contaminated by winds and radiation-driven outflows. A strong outflow can broaden the line without representing orbital motion, and it can shift the line centroid blueward. Analysts look for asymmetry, blue shift, and profile shapes that betray non-virial components. They may downweight CV when the line looks like it is being pulled by a gale. Those diagnostics are not cosmetic because a wind can add velocity that is not bound to the black hole. If the gas is being accelerated outward, then the line width measures a mix of orbit and escape. In that case, the virial formula can overestimate mass unless the wind contribution is modelled or excluded. The spectrum can be honest while still being ambiguous about the cause. Mg Sekub is often considered more stable as a virial tracer because it tends to arise in somewhat lower ionization gas. It can still be affected by complex dynamics, but it is usually less wind-dominated than CV. Using multiple lines helps reveal systematics, because different regions should not disagree wildly if gravity is the main driver. When they do disagree, the disagreement itself becomes a clue. For TON 618, published estimates converge on an enormous mass, often quoted near 6.6 times 10 to the 10 solar masses. Different calibrations and line choices shift the number, and different authors adopt different geometry factors, yet they do not shrink it to ordinary, and the object stays in the top tier of known black hole masses. The argument is not about whether it is big, but about exactly how big. It is worth pausing on what converge means in a field built from indirect inference. The estimates do not match to the last digit because they cannot, but they cluster in the same frightening neighbourhood. When independent methods land on the same scale, the uncertainty starts to look like a boundary rather than an escape hatch. The scatter becomes a fence around a monster, not a door out of the room. The geometry factor is the quiet variable that can move the answer without changing the data. The broadline region is not a perfect sphere, and it may be flattened, clumpy, or partially supported by turbulence. If we view a disk-like region face-on, line widths can look narrower than the true orbital speeds. That is a projection effect, not a change in the underlying gravity. Orientation can therefore bias virial masses, and the bias is baked into projection. A face-on system can be underestimated because most motion is in the plane of the sky, while an edge-on system can be overestimated. Astronomers try to infer orientation from radio properties, line shapes and population statistics. They are doing for distant quasars what sailors once did with stars, inferring direction from indirect cues. Radio jets, when present, can act like a compass needle because they often align with the black hole's spin axis. If the jet points toward us, the system is likely closer to face-on and line widths may be suppressed. TON 618 is not dominated by a glaring jet, but orientation still matters in subtler ways. Even without a bright jet, the host environment can hint at viewing angle. Still, orientation alone cannot easily erase an order of magnitude, and that is the key constraint. It can move the estimate by factors of a few, depending on geometry assumptions and how flat the broadline region is. For TON 618, a factor of a few still leaves a monster. The ceiling may shift, but the floor remains uncomfortably high. There is also the question of how the continuum luminosity is measured, because luminosity is the input to the radius scaling. Quasar spectra are not flat, and dust can redden and dim the light, especially in the ultraviolet. Host galaxy contamination is usually small for such luminous quasars, but absorption and calibration still matter. Even the intergalactic medium can nibble at the blue end of the spectrum. Observers must correct for the fact that we measure flux, not luminosity, and flux depends on distance and cosmology. They adopt a cosmological model to convert redshift into luminosity distance, and that choice introduces a small but real systematic. The correction is not usually dominant, but it is part of the accounting. In the background, the expansion history of the universe quietly enters the mass estimate. Analysts apply bolometric corrections to estimate total radiated power from a measured band, because quasars emit across the spectrum. Those corrections are based on typical quasar spectral energy distributions built from large samples. Extreme objects may deviate, and deviations can shift inferred luminosity and radius. A slightly different ultraviolet slope can ripple through the calculation. Even so, the broad picture remains stubborn, because it is supported by two independent observables. TON 618 is extremely luminous, and its lines are extremely broad, and those facts are difficult to fake simultaneously. Together they push the virial mass high under any reasonable calibration. It is like trying to argue a hurricane is gentle while the wind gauge and the pressure drop agree. A second mass constraint comes from brightness itself, through the Eddington limit, which is a balance sheet for forces. The Eddington luminosity is the point where radiation pressure on ionized gas balances gravity's inward pull. If a source shines above that limit steadily, the light should blow away the inflow that feeds it. The limit is derived from simple physics, but it governs some of the universe's most violent objects. The Eddington limit is not a moral rule and not a magical ceiling, but it is a useful yardstick for plausibility. It ties luminosity to mass, because heavier black holes can hold onto gas against stronger radiation. The limit scales linearly with mass, so luminosity implies a minimum mass if the source is not wildly super Eddington. In plain language, more weight lets you shine harder without pushing your fuel away. In simple terms, photons push outward and gravity pulls inward, and the contest is mediated by electrons. In ionized gas, electrons feel the radiation pressure strongly through scattering, and they drag ions with them through electric forces. When the push equals the pull, the flow becomes self-regulating. The key interaction is Thomson's scattering, which is mundane in a lab and decisive near a quasar. That self-regulating behavior is why quasars do not usually run away indefinitely. If the luminosity rises, radiation pressure can reduce the inflow, which can then reduce luminosity. The feedback is messy in detail, but the basic idea is a thermostat built from light. The thermostat does not keep things calm, it keeps them from becoming impossible. TON 6-18's luminosity is so high that it demands a large Eddington mass scale, even before we discuss line widths. If it radiates near the Eddington rate, the mass must be enormous. If it radiates below Eddington, the mass must be even larger to allow that luminosity comfortably. Either interpretation points toward a black hole that is already heavyweight. If it radiates above Eddington, then the accretion physics must be unusual, and the geometry must help the radiation escape. Super Eddington flows can occur when radiation escapes anisotropically, or when the disk becomes thick and funnel-shaped. But even then, there are limits on how far and how long the excess can persist. A brief flare is one thing, a sustained quasar is another. A thick disk can trap photons, letting matter fall inward while radiation leaks out along preferred directions. That can make a source appear brighter from some angles without requiring the entire flow to defy the Eddington balance. Yet such configurations still struggle to sustain extreme excess for long cosmic intervals. The universe can cheat, but it rarely cheats forever. So Eddington arguments do not replace virial estimates, but they triangulate them from a different physical principle. A virial mass that implies a plausible Eddington ratio looks more credible, because it does not require special pleading. A mass that would require absurdly super Eddington emission looks less stable as an interpretation. The two approaches are like independent auditors checking the same ledger. For TON 6-18, the Eddington ratio is often inferred to be of order unity or below, depending on bolometric correction and line choice. That is unsettling because it suggests the luminosity is not an extreme cheat or a narrow beam aimed at us. It suggests the mass is genuinely huge rather than artificially inflated by orientation tricks. The quasar seems bright in a straightforward, physically expensive way. This is where the investigative tone sharpens, because we have two different rulers pointing the same way. One ruler is kinematics, where gravity sets speeds in the broadline region. The other ruler is radiation balance, where gravity must defeat photon pressure if accretion is to continue. When both rulers agree, the room for denial narrows. Neither ruler is perfect, and both carry systematics that can widen error bars. But they are based on different physics and different observables, which makes agreement meaningful. Agreement between them is not proof, but it is pressure, and pressure is what science uses to corner a number. The number may still wobble, yet it cannot wander anywhere it wants. Now translate the mass into a horizon scale, because numbers alone do not land emotionally in the mind's eye. The Schwarzschild radius is proportional to mass, about 3 kilometers per solar mass, and that proportionality is one of relativity's cleanest gifts. Multiply that by tens of billions, and the event horizon becomes solar system sized. The mind resists, so we give it a picture. For a non-rotating black hole, the radius would be roughly 200 billion kilometers, depending on the adopted mass. That is on the scale of thousands of astronomical units, comparable to the outer reaches of our system where sunlight is thin. It is not a point, it is a boundary with volume-like presence in any visualization. In an animation, it would swallow the orbits of the planets as a mere inner detail, Imagine a dark sphere drawn over a star field, blotting out constellations behind it, and then imagine that sphere spanning the scale of distant comets. The comparison is not literal, because TON 618 is far away and does not cover our sky. It is a mental conversion from mass to distance. The goal is not fear, but comprehension. A common comparison is light travel time across the diameter, because time is easier to feel than kilometers. For TON 618, light would take on the order of weeks to cross the horizon scale, depending on the exact mass and spin. That statement is not about danger, it is about geometry. It tells you how large the no-return surface is in the only units that feel universal. It does not mean the black hole is expanding toward us, and it does not mean space is being swallowed like a vacuum cleaner. It means the region of no return is so large that even light needs days to traverse it. The comparison is a way to convert mass into a distance we can picture. The gravity is intense near the horizon, but it does not reach out like a hand. Spin complicates the picture, because a rotating black hole has a smaller horizon radius and a larger ergosphere where spacetime is dragged. Real quasars likely host spinning black holes because accretion tends to add angular momentum over long periods. But spin changes the radius by factors, not by orders of magnitude. The monster remains a monster, even when it is rotating. In a rotating case, the innermost stable circular orbit moves inward, which can raise radiative efficiency and alter growth rates. That matters for the origin story, because efficiency determines how much mass is converted into light. Here, it matters mainly because it tweaks the scale comparisons without rescuing us from enormity. A more efficient engine shines more per kilogram, which changes the growth clock. The broadline region sits far outside the horizon, and that separation matters for the credibility of virial methods. The gas producing the broad lines is not skimming the event horizon in a relativistic blur. It is orbiting at distances where classical gravity approximations still guide intuition, even if relativity lurks in the background. The velocities are extreme, but the physics is still legible. That is why virial methods work at all, and why they are used across cosmic time. We're not trying to model quantum gravity at the boundary, where theory becomes fragile. We are measuring orbital motion in gas that is still outside the deepest relativistic zone, where Newton's logic remains a good first language. The method is humble, and that humility is its strength. Still, the environment is not quiet, and the line profiles remember that turbulence. Radiation, magnetic fields, and winds can alter cloud dynamics and sculpt the wings of emission lines. The broad line region may be partly bound and partly outflowing, and the mix can vary by line and by epoch. In a visualization, you would see not a tidy ring, but a storm of glowing knots. Some models picture clouds confined by magnetic pressure, while others favor a continuous wind launched off the disk surface. Both pictures can reproduce broad lines, and both can produce variability. The uncertainty is not whether gas is moving fast, but why it is moving that way. That why becomes the lever that can shift a mass estimate. So uncertainty must be stated clearly, because precision is not the same as accuracy. Virial masses have typical scatter, often quoted around 0.3 to 0.5 dex depending on line and calibration. That corresponds to factors of 2 to 3, sometimes more in individual cases. The scatter is not failure. It is the cost of measuring a distant engine with a spectrum. Systematics include orientation, because line width depends on viewing angle and on how flattened the emitting region is. They include line selection, because different ions trace different regions and different dynamics. They include calibration choices, because the radius to luminosity relation is empirical and has intrinsic scatter. Each systematic is small alone, yet they can align in unfortunate ways. Even the definition of line width can introduce subtle differences, because dispersion and half maximum widths respond differently to wings. A line with a strong wing can inflate one metric more than the other. Analysts choose consistent definitions to match the calibration they are using, because mixing conventions can quietly bias results. In the background, statistical choices become physical consequences. There is also the possibility of lensing, because gravitational lensing can boost apparent luminosity without changing intrinsic mass. Strong lensing usually leaves telltale multiple images, arcs, or distortions, and TON 618 is not a clean lens candidate in available imaging. Weak lensing could still contribute modest amplification, but modest is not enough. A small boost cannot explain a spectrum that already screams fast gas. There is also the possibility of an unusual spectral energy distribution, because bolometric corrections assume a typical quasar shape. If TON 618 emits more in unobserved bands than expected, luminosity could be misestimated. But the mass estimate is not driven by luminosity alone, and line widths do not care about our bolometric bookkeeping. The spectrum's breadth is stubbornly indifferent to our assumptions about missing photons. Even if every uncertainty pushes in the same direction, the conclusion remains extreme, and that is the uncomfortable stability of the result. Reduce the mass by a factor of 3, and it is still tens of billions of suns. Reduce it by a factor of 10, and it is still among the largest known. The error bars can shrink the monster, but they cannot domesticate it. That robustness is the real story of the measurement, and it is why TON 618 keeps returning in discussions. The headline number can shift as calibrations evolve, but the category does not. TON 618 remains a stress test for how black holes grow, because it sits at the edge of what our growth clocks allow. It is the kind of object that forces theorists to check their assumptions twice. Now connect the measurement back to the central question. Because the mass is not a trophy and not a curiosity, if the mass is real, then the early universe assembled it quickly, and quickly has a strict meaning in cosmology. That pushes against the growth clock set by Eddington limited accretion and by radiative efficiency. The clock is not metaphorical, it is exponential math. The Eddington limit implies a characteristic exponential growth timescale for black holes, often described in terms of e-folding or doubling times. Starting from small seeds, reaching tens of billions requires many doublings, and each doubling takes time. The early universe does not offer unlimited time, especially at the redshifts where such luminous quasars appear. When you do the arithmetic, the margins feel uncomfortably thin. This is the arithmetic behind the unease, and it is not a matter of taste. If a black hole grows by steady, near Eddington accretion with typical efficiency, it follows a predictable curve. To reach the TON 618 scale early, that curve must be bent, accelerated, or started from a higher baseline. The measurement turns into a demand for a backstory. So the tension tightens, and the mystery becomes more specific rather than more vague. Either the seed was already massive, or the accretion was super Eddington for long periods, or mergers stacked mass rapidly in dense environments, or our assumptions about radiative efficiency and feedback are incomplete under early conditions. The options are constrained, which is what makes them interesting. Each of those possibilities is already hinted at by the measurements themselves, because the measurements constrain what is plausible. A low Eddington ratio suggests the quasar is not desperately overfeeding at the moment we see it. That raises a question. If it is not straining now, when did the most aggressive growth happen? Did the feast occur earlier, hidden behind dust, or in a phase we rarely catch? This is where the story turns from measurement to origin, because the number forces the next question. We can argue about factors of 2, and we should, because rigor lives in those factors. But we cannot argue away the need for a fast path, and that need is the narrative engine. The mass is not the end of the chapter, it is the door it opens. The unsettling implication is not that TON 618 is coming for us, and not that it threatens anything nearby. Its light is coming, and that light carries a record of what the early cosmos could do when gas was abundant and structures were young. The record says runaway extremes were possible, and our neat timelines may not be safe. It invites a broader question. How many such giants formed, and how many we simply cannot see? As the camera lingers on the spectrum, those broad lines become more than data products. They become the blurred handwriting of matter in orbit, tracing a gravity well too distant to image. And the question hangs in the dark between peaks. How did the universe build the hand that wrote this? In the silence after the calculation, the spectrum feels less like a graph and more like a confession. Chapter 4 follows that implication into formation scenarios, using the measured mass as a constraint rather than a conclusion. We take the number seriously, then ask what kind of early universe could build it without breaking the known rules. If TON 618 is not an error, then the worst thing is not the whole. The worst thing is what it implies about the universe's capacity for rapid, hidden growth. TON 618's mass is not just a big number. It is a deadline problem written into the early universe. When we say tens of billions of suns, we are not only describing weight, we are describing a schedule. one that begins almost as soon as the cosmos becomes transparent. Chapter 3 gave us a scale, and the scale points to tens of billions of suns. Chapter 4 asks the only question that follows: how does anything get that massive that early without breaking the growth rules? The clock starts after recombination, when the universe cools enough for neutral atoms to form. Before that moment, electrons and protons scatter light constantly, and the cosmos behaves like a glowing fog. In that plasma era, photons cannot travel far without being deflected. Space is filled with a hot, bright soup, and information cannot move cleanly from one region to another. Then the fog thins, almost suddenly on cosmic terms, and photons begin to free stream. The cosmic microwave background marks that transition, and it locks in the initial conditions for structure. Visually, it is like a curtain lifting on an unfinished stage. The light we see today as the microwave background is the afterimage of that lift, an all-sky photograph of the universe at about 380,000 years old. The picture is not smooth, and that is the point. It contains tiny hot and cold speckles that correspond to slightly denser and slightly thinner patches of matter. Those faint temperature mottles in the background are not decoration. They encode tiny density ripples at the level of tens of parts per million, which gravity will spend hundreds of millions of years amplifying. The ripples are small, but they are coherent across enormous distances. They are the seeds of the cosmic web, and they are the reason galaxies form where they do. After recombination, there are no stars yet, only dark matter, scaffolding, and cooling gas. The gas is mostly hydrogen and helium, and it is smooth enough that nothing shines. This dark age is not empty, but it is visually silent. If we could watch it, we would see gravity working without fireworks, pulling gently on matter that has not learned to glow. Dark matter, however, does not need to cool, and it does not feel radiation. It begins clumping earlier, building a web of halos and filaments that will later guide ordinary matter. Baryons fall into those potential wells, but they arrive with pressure and motion. They must radiate energy away to settle, and in a metal-free universe that is a slow, picky process. Gravity amplifies tiny density ripples, but early growth is slow and hierarchical. Small halos form first, then merge into larger ones, and the process resembles a branching river system rather than a single collapse. The hierarchy matters because it sets the cadence of opportunity. If you need a giant black hole early, you need large, deep wells early, and those are rare at first. In simulations, the cosmic web appears as luminous threads against blackness. Filaments feed knots, knots merge into nodes, and the nodes become the cradles of the first galaxies. The filaments are not just lines on a map. They are dynamic streams, and they deliver gas with direction, speed, and angular momentum that can either feed a nucleus or miss it. Yet even with that scaffolding, baryonic gas has to do something difficult. It must shed energy and pressure support, and it must do it without already having metals or dust. Cooling is the hidden bottleneck because hot gas resists collapse. To make stars or a black hole seed, the gas must drop in temperature, increase in density, and then fragment or funnel inward. The first luminous objects arrive when gas can finally cool and fragment efficiently. That likely happens in small halos, where molecular hydrogen enables the first star formation. Molecular hydrogen is a fragile coolant, and that fragility matters. In a metal-free universe, H2 forms slowly through rare chemical pathways, and it can be destroyed by ultraviolet light from the first stars. The chemistry is almost improvisational, built from traces of free electrons left after recombination. Those electrons catalyze reactions that assemble H2, and the resulting molecules radiate away heat in discrete lines. So the first star-forming halos are special places. They are massive enough to hold gas, cold enough to let H2 survive, and quiet enough that turbulence does not tear the cloud apart too early. They are also vulnerable places because the first light is disruptive. The first stars do not merely illuminate their cradles, they rewrite the conditions for the next collapse. Those first stars are called population threed, and they are expected to be massive and short-lived. They burn fast, explode or collapse, and they seed the first heavy elements. Massive here is not a poetic word. Without metals to help cooling, the gas fragments into fewer larger clumps, and theory often favours stars tens to hundreds of solar masses. In that regime, radiation pressure and ionization shape the protostar's growth. Accretion onto the star can be choked by its own ultraviolet output, yet the initial clumps are so large that the final masses can still be extreme. a star that heavy lives like a match in a gale. Its core temperature rises, fusion runs violently, and the lifetime can be only a few million years, brief even by stellar standards. When such stars die, they change everything around them. Their ultraviolet radiation ionizes nearby gas, their supernovae drive shocks, and their ashes enrich the medium with carbon, oxygen, and silicon. The explosions carve bubbles in the surrounding medium, and the shock fronts compress some regions while evacuating others. In a young galaxy, those bubbles can overlap, turning the interstellar gas into a patchwork of hot cavities and dense shells. Those first metals are small in quantity, but enormous in consequence. Metals provide new cooling lines, dust grains catalyze molecules, and the next generations of stars can form more easily and in smaller masses. This is the universe learning efficiency. Once heavy elements exist, gas can cool to lower temperatures, fragment into many smaller cores, and build a more familiar stellar population. The first galaxies assemble from mergers of smaller halos and from gas inflows along filaments. In that era, everything is compact, turbulent, and rapidly changing. Picture a young galaxy not as a calm spiral, but as a crowded construction site. Gas streams collide, clumps shear past each other, and star formation ignites in bursts that can flare and fade quickly. The gravitational potential wells are shallow compared to modern galaxies. That means feedback from stars and black holes can reshape the whole system, not just the central region. A single starburst can heat or expel a significant fraction of the gas, and a single energetic episode can delay the next collapse. The early universe is a place where small differences can cascade into major outcomes. Somewhere inside this sequence, the first black hole seeds must appear. The problem is that TON 618 implies the seeds did not just appear. They grew with astonishing speed. The word seed can sound gentle, but it hides a brutal requirement. Whatever forms first must survive, must stay fed, and must avoid being kicked out of its own nursery. Start with the simplest seed scenario, a stellar remnant black hole from a massive star. That gives you tens of solar masses, maybe a few hundred in optimistic cases. This is the familiar endpoint of stellar evolution. A massive star exhausts its fuel, the core collapses, and if the explosion fails or is weak, a black hole forms at the center. In detail, the core's pressure support vanishes when nuclear burning can no longer counter gravity. The collapse drives densities and temperatures so high that neutrinos carry away energy, and the outer layers either rebound or fall inward. But a seed that's small faces exponential arithmetic that is not forgiving. Every doubling takes time, and you need many doublings to reach billions. Exponential growth is deceptive because it feels fast only after it has already succeeded. In the early stages, when the mass is small, each doubling adds little absolute mass, and the clock keeps running. Population 3 stars could leave heavier remnants if they collapse directly without a supernova. Even then, the seed is still tiny compared to the endpoint. There is also a narrow mass range where pair instability can disrupt a star completely. In those cases, the star leaves no black hole at all, and the seed pathway simply vanishes. Pair instability is a particularly cruel twist, because it targets very massive stars. At high core temperatures, photons turn into electron-positron pairs, pressure drops, and the star can detonate itself from the inside. So even the first generation does not guarantee a robust supply of remnants. The early universe may produce some seeds, but it can also erase them through the very physics of massive stellar interiors. Dense star clusters offer a second route, through runaway collisions and mergers. Many stars can sink to the center, merge repeatedly, and form an intermediate mass seed. The key mechanism is mass segregation, where heavier stars lose energy through interactions and drift inward. In a crowded cluster core, close encounters become common, and collisions can become inevitable. As the core grows denser, a runaway can begin. One object becomes slightly more massive, then its gravity makes it collide more often, and the process accelerates until a single heavy remnant dominates. Visually, it is like watching a swarm tighten into a whirlpool. Individual orbits blur, the center becomes a bright knot of encounters, and then the knot collapses into something darker and more compact. That cluster route might produce seeds of thousands, maybe tens of thousands of solar masses. It helps, but it still leaves a long climb to tens of billions. And clusters are not isolated laboratories. Gas inflows, stellar winds, and supernovae can blow out the cluster's fuel, and the cluster itself can be disrupted by tidal forces in a merging galaxy. A third route is direct collapse, where a pristine gas cloud avoids fragmenting into normal stars. If the gas stays hot and coherent, it can collapse into a massive object. Here the visual changes from many small sparks to one dark plunge. Instead of breaking into stars, the cloud contracts as a whole, building a central object that can become a black hole quickly. The physics hinges on keeping the gas near 10,000 Kelvin, where atomic hydrogen cooling operates but fragmentation is suppressed. If the cloud stays warm and dense, it can funnel inward before it breaks into many stars. Direct collapse can make seeds of 100,000 to 1 million solar masses. That is the first scenario that meaningfully shortens the timeline. A seed of 1 million solar masses is not close to 60 billion, but it changes the math. It reduces the number of required E-foldings, and it relaxes the demand for perfect feeding. But direct collapse is not easy to arrange in the early universe. You need strong radiation backgrounds to suppress cooling, and you need special environments to avoid fragmentation. The usual story invokes intense Lyman. Werner ultraviolet radiation, which breaks apart molecular hydrogen. Without H2, the gas cannot cool to low temperatures, and it resists fragmenting into ordinary stars. That requirement implies a neighbourhood with nearby star formation, yet not so much pollution that metals and dust trigger fragmentation anyway. It is a narrow ecological niche, and the early universe must produce it repeatedly. Even if direct collapse happens, it must happen early and often enough to explain the observed quasar population. Otherwise, it becomes a rare exception, not a solution. So seeds matter, but seeds are only the first constraint. The next constraint is how fast a black hole can eat once it exists. Accretion is not a simple vacuuming process, because infalling gas must lose angular momentum. Disks form, and disks radiate, and that radiation pushes back. Angular momentum is the hidden gatekeeper. Gas in a galaxy is not falling straight in. It is orbiting, and to move inward it must transfer that orbital motion outward through torques and friction. As the gas spirals down, it heats up through viscosity and shocks. The inner disk can reach temperatures where it glows in ultraviolet and X-rays, turning gravity into light with startling efficiency. That glow is not incidental, it is the signature of conversion. A black hole does not shine by itself, but the disk around it can outshine an entire galaxy, while the whole gains mass in silence. The Eddington limit is the basic balance sheet for that pushback. At a certain luminosity, radiation pressure on electrons balances gravity's pull on the ionized gas. This balance is not mystical, it is a simple competition of forces. Gravity pulls inward on protons and electrons, while photons scatter off electrons and push outward, and the coupling drags the ions along. If you try to feed faster in a spherical, steady way, the light fights the inflow. The engine becomes self-regulating because brightness can shut down its own fuel supply. The limit depends on mass, which creates a strange symmetry. Bigger black holes can shine brighter without blowing themselves apart, yet they still face the same proportional constraint on how quickly they can grow. The Eddington limit is not a perfect ceiling, but it is a strong attractor. Many accreting systems hover near it because the feedback is immediate. Historically, this idea emerged from early 20th century work on stellar atmospheres. The same physics that limits how bright a star can be without blowing off its outer layers also constrains luminous accretion flows. To connect that limit to growth, you need radiative efficiency. Efficiency is the fraction of rest mass converted into light as gas spirals inward. In plain terms, efficiency tells you how much of the meal becomes glare. If the disk is efficient, the black hole shines brilliantly, but it gains less mass per unit inflow. Higher efficiency makes a brighter quasar for the same mass inflow. It also slows mass growth, because more of the inflowing mass energy leaves as radiation. That trade is the heart of the growth problem. The more luminous and efficient the engine, the harder it is to gain mass quickly. Efficiency depends on the inner edge of the disk, which depends on spin. A rapidly spinning black hole allows stable orbits closer in, extracting more gravitational energy and raising the radiative yield. Spin is not just a parameter, it is a record of how the hole was fed. A long, coherent disk can spin it up, while chaotic episodes can keep it from reaching maximal rotation. The salpeter time is the characteristic E-folding time for Eddington limited growth. It is the doubling clock that turns accretion physics into a timeline. With typical efficiencies, The Salpeter time is tens of millions of years per E-fold. That sounds short, until you count how many E-folds you need. A useful way to picture it is a staircase in the dark. Each step is fixed by physics, and you cannot skip steps unless you change the rules of feeding. From 100 solar mass seed to a billion solar mass black hole takes many E-foldings. From there to tens of billions takes several more. Now place that math into the cosmic window available at high redshift. The earliest quasars appear when the universe is under 1 billion years old. That under 1 billion includes everything. The first halos, the first stars, the first metals, the first galaxies, and the first stable pathways to sustained accretion. The schedule is crowded long before the black hole reaches its peak mass. It is also a schedule with delays that are easy to underestimate. A seed may form quickly, but it still needs a dense, sustained gas reservoir, and that reservoir must survive the violence of early star formation. That means the entire growth history must fit inside a narrow slice of cosmic time. It must also survive interruptions, because real galaxies do not feed steadily. The simplest story assumes continuous near-Eddington accretion from very early times. That is already a demanding assumption, because gas supply is not constant. Galaxies form in bursts and inflows can be clumpy and chaotic. Star formation competes for the same gas, and supernovae can stir and heat the reservoir. In the early universe, cold streams can penetrate deep into halos, delivering fuel along filaments. Yet those streams can also shock, fragment, or be disrupted by feedback, turning a steady pipeline into a sputtering faucet. Even if gas reaches the nucleus, it must cross many scales and shed angular momentum. Bars, spirals, turbulence, and instabilities must keep funneling fuel inward. This is a multi-stage descent, like water moving through a series of locks. Gas must move from kiloparsec scales to hundreds of parsecs, then to parsecs, then to fractions of a parsec where the accretion disk takes over. At each stage, something can stall it, star formation can consume it, feedback can heat it, and gravitational torques can change direction as the galaxy reorganizes. Visually, the journey is almost absurd in scale. Gas must travel from regions larger than a galaxy's core down to distances comparable to the solar system, and it must do so while remaining cold enough to stay bound. Then comes the next constraint, the quasar's own feedback. The act of shining changes the environment that makes shining possible. Quasar radiation heats surrounding gas and increases pressure support. Hotter gas is harder to capture, and it can be driven outward in winds. The heating can create an ionized bubble around the nucleus, and that bubble changes the cooling balance. Gas that might have condensed into a dense disk can remain diffuse, hovering instead of falling. Powerful outflows can expel the very material that would have fed the disk. In that regime, the quasar becomes an engine that starves itself. Observationally, these winds can reveal themselves in broad absorption lines and shifted emission features. The spectrum becomes a weather report, hinting at storms driven by radiation and magnetic fields. The lines are not just pretty, they are kinematic fingerprints. They tell us gas is moving at thousands of kilometers per second, and they imply momentum transfer that can reshape a young galaxy's central regions. Jets add another channel for feedback, carrying energy far beyond the nucleus. They can shock the interstellar medium and prevent cold gas from settling. In images and radio maps, jets look like narrow spears. They drill through the galaxy, inflate lobes, and deposit energy in regions that the accretion disk will never directly touch. Feedback is not always purely negative, and it can compress gas in some regions. But for sustained accretion, strong feedback is usually a break. It can trigger star formation in a shell while starving the center, an ironic redistribution of fuel. The galaxy lights up in new places, while the black hole's own pantry empties. This is where the investigative tone sharpens, because the constraints stack rather than cancel. Small seeds demand long growth, and long growth demands steady feeding. Steady feeding demands a stable gas supply, but the quasar's output destabilizes that supply. The engine's success makes its future success less likely. So theorists look for ways to bend the Eddington story without discarding physics. One route is super-Eddington accretion, where geometry changes the balance. In thick disks, photons can be trapped and advected inward with the flow. Radiation escapes through funnels, and the inflow can exceed the naive Eddington rate. This is not a free lunch, but it is a loophole. If the disk is puffed up by pressure, light can leak out along the poles while gas continues to pour in along the equator. In that picture, the quasar becomes anisotropic, bright in some directions and dimmer in others. That matters because feedback depends on where the energy goes, and funnels can spare parts of the inflow for a time. Super Eddington phases can grow mass faster than standard thin disk accretion. The question is whether they can last long enough and occur early enough. Short bursts help, but the arithmetic still demands persistence. A few million years of excess feeding is impressive, yet the timeline for TON 618 asks for repeated episodes that do not permanently blow away the fuel. Sustained Super Eddington growth also risks stronger feedback, because the system is even more luminous. The faster you eat, the harder you push back. Another route is lower radiative efficiency, which lets more mass stay in the black hole. But lower efficiency often implies different disk states that may be unstable. Some flows become radiatively inefficient because energy is carried inward rather than radiated away. Yet those flows can be hot and thick, and they may not couple to the surrounding gas in the same way as a bright thin disk. Spin complicates this, because spin raises efficiency for thin disks. A rapidly spinning hole shines more per kilogram, which slows growth for a given luminosity. Spin is also a memory of history. Coherent accretion in one direction tends to spin a black hole up, while chaotic accretion and mergers can keep spin lower. Each pathway leaves a different signature in efficiency. If early black holes spin up quickly, the growth problem gets worse. If they stay low spin, growth is easier, but the conditions must explain that. Now add mergers, the other major way to gain mass without radiating it away. Galaxies merge frequently in the early universe, and their nuclei can pair up. In a young cosmos, mergers are not rare accidents. They are part of the assembly line, as small halos collide and larger systems are built from repeated impacts. When two galaxies merge, their central black holes sink toward the center through dynamical friction. Eventually they form a bound binary. Dynamical friction is gravitational drag, created as the moving black hole stirs a wake of stars and dark matter behind it. That wake pulls back, bleeding orbital energy until the black holes meet. A binary can harden by interacting with stars and gas, and then gravitational waves take over. The final coalescence converts some mass energy into gravitational radiation. Gravitational waves are not metaphorical here. They are ripples in space-time itself, carrying energy away at the speed of light, and they become dominant when the separation shrinks to tiny scales. That energy loss is small compared to the total mass, but it is not zero. Mergers do not add perfectly, and recoil kicks can even displace the remnant. The recoil comes from asymmetry in the emitted waves. If the system radiates momentum unevenly, the merged black hole can be kicked like a cannon recoil, sometimes fast enough to wander its host. In the early universe, wandering is dangerous. A displaced black hole can be removed from the densest gas, and a few tens of millions of years of starvation can erase the advantage of a merger. Mergers help because they can jump the mass upward in discrete steps. But mergers require that many massive seeds already exist in the same region. They also require that those seeds remain in the galactic center long enough to meet. In shallow potentials, a strong kick or a violent interaction can exile a growing black hole from the very gas it needs. Mergers also take time, and early galaxies are small and gas-rich in ways that complicate binary evolution. The so-called final parsec problem can delay coalescence. At separations of about a parsec, the binary can run out of stars on intersecting orbits, and the hardening can stall. The system needs a fresh supply of interactions, or it lingers while the universe ages. Gas can solve that delay by torquing the binary and extracting angular momentum, but gas can also fragment into stars, changing the dynamics again. Even in optimistic merger trees, you still need accretion between mergers. Mergers alone struggle to build the largest masses fast enough, so the growth story becomes a tight corridor. Seeds must be big, feeding must be near maximal, and feedback must not shut the process down. Now place TON 618 at the far end of that corridor. It is not just an early quasar, it is an extreme endpoint of the distribution. In visual terms, imagine a histogram of black hole masses at high redshift. Most objects cluster in a plausible range, and then TON 618 sits out near the edge, where the tail becomes a cliff. If TON 618 really sits near 60 billion solar masses, then the corridor may be too narrow. Either the early universe had wider doors, or we misread the signs. One possibility is that early environments were denser and more gas-rich than our simple models assume. Higher densities shorten inflow times and raise duty cycles. A denser environment means shorter cooling times and faster gravitational collapse. It also means more frequent interactions, which can torque gas inward and keep the nucleus supplied despite turbulence. Another possibility is that metal-free gas behave differently, changing cooling and fragmentation. If fewer stars formed early, more gas could reach the nucleus. That is an uncomfortable thought, because it implies a different balance between light and darkness in the first galaxies. If star formation is delayed, the galaxy stays dimmer, yet its central black hole can quietly gain mass. Another possibility is that radiation fields and magnetic fields shaped accretion in ways we have not fully captured. The early universe may have favoured thick disks. Magnetic fields can transport angular momentum through magnetorotational instability, and that can change how efficiently gas moves inward. In a thick disk, the geometry can hide some radiation and reduce the effective pushback, at least for a while, or the mass estimates could be biased at the extreme end, even if the methods work well on average. Broad lines can include wind components, and scaling relations can bend. At the highest luminosities, the broadline region may not behave like a simple virialized cloud system. If winds contribute to line widths, the inferred mass can be inflated, and the uncertainty grows precisely where the stakes are highest. But the tension does not vanish by wishing for smaller error bars. Even a reduced mass leaves TON 618 among the fastest growth demands we know. This is where the story turns from accounting to unease, because the numbers point to missing context. The early cosmos might not have been a gentle nursery. Early structure formation might have produced rare, overfed nodes where gas streams converged. In those nodes, black holes could grow in bursts we rarely observe. In simulations, such nodes look like bright intersections in the cosmic web. Multiple filaments feed the same region, and gas arrives with enough momentum and density to keep refilling what feedback tries to remove. The visual is almost anatomical, like arteries converging on a beating heart. The filaments pulse with inflow, and the central region flashes as star formation and accretion take turns dominating the light. If that is true, TON 618 is not a freak accident. It is a signpost for a population that is hard to detect with older instruments. Older surveys are biased toward unobscured bright phases, and they can miss growth hidden behind dust and gas. The most rapid feeding might be brief, shrouded, and visible only in infrared or through indirect signatures. That brings us back to the central question. Because growth history is part of identity. What is TON 611 really if it violates the expected timetable? If it is a standard black hole, then our early universe assumptions about seeds and feeding are incomplete. If it is not standard, then the word black hole may be hiding something. Either way, the worst thing coming is not the object itself. The worst thing is what its light forces us to admit about cosmic speed limits. A quasar is a beacon, but it is also a ledger. It records how much mass has been converted into energy, and it tells us that the conversion happened quickly enough to beat the universe's own clock. There is a quiet philosophical edge to that ledger. If gravity can assemble such extremes so early, what else in the young universe reached maturity before we expected it to even begin? This is where the story turns again, because we are no longer alone with one monster. New telescopes are expanding the sensors of early luminous objects. JWST pushes deeper into infrared, where high redshift light is shifted and where dusty growth phases can be revealed. It is finding surprisingly mature galaxies at early times. In JWST images, the early universe is not a sparse field of tiny smudges. It is crowded with compact systems, some with structured shapes, implying that assembly and star formation were already well underway. Those shapes are clues, because structure implies time. Disks, bulges, and clumps suggest repeated cycles of inflow and feedback, and they suggest that the early universe was not merely forming objects but organizing them. A richer early universe makes the growth problem sharper, not softer. More early structure means more early fuel, but it also means more early contradictions. If galaxies are forming stars rapidly, they are consuming gas that black holes might need. If galaxies are already massive, then the processes that built them must be efficient, and the same efficiency may apply to black hole growth, yet it must still obey feedback limits. So Chapter 4 ends on a pressure point rather than a resolution. TON 618 is the extreme case that forces a choice between revised conditions and revised physics. If the timeline is wrong, the early cosmos must be stranger than we thought. And if it is stranger, then the message arriving now is only the beginning. TON 618 is a single data point with a long shadow, and for years that shadow fell across an almost empty map. JWST turns that shadow into a crowd, then forces us to ask what kind of crowd it is. For decades, the first billion years were a thinly sampled era, more like a coastline drawn from a few sightings than a surveyed continent. We had a few bright quasars, a few lensed galaxies, and many simulations filling the gaps. The early universe was theory-heavy because the light was shifted out of reach, and because the objects were small, young, and brutally far away. Even the most ambitious deep fields were limited by exposure time, detector noise, and the simple fact that the sky is not generous. In that era, a single confirmed object could steer an entire set of models simply because there were so few anchors. In the older surveys, the most informative photons were the hardest to catch. The ultraviolet light from hot, massive stars carried clues about star formation rates and stellar ages. The optical continuum carried breaks and slopes that could anchor a galaxy's history. Yet in the first billion years, those same photons were stretched by cosmic expansion until they slid into infrared bands. That stretching is not subtle at high redshift, because the scale factor changes quickly in a young universe. A rest frame ultraviolet feature at 150 nanometers can arrive in the near-infrared, where the atmosphere glows and older instruments struggled. Redshift does not just move objects farther away, it moves their ultraviolet and optical light into infrared wavelengths where older telescopes struggled, especially when detectors were noisier and mirrors were smaller. The earliest galaxies were not only faint, they were speaking in wavelengths we could barely hear, and they were doing it through a fog of intervening hydrogen. That fog is not a metaphor, because neutral hydrogen absorbs and scatters short-wavelength light with ruthless efficiency. Before reionization completed, the intergalactic medium could erase the very lines we wanted most. Visually, this is a simple transformation with a complicated consequence. Imagine a bright blue ember carried away on a river that lengthens its light into deeper, redder tones. The ember is still there, but the colour that once made it obvious is now hidden in a different part of the spectrum. In practice, that means the same galaxy can be nearly invisible in optical images, then appear as a compact glow in the near-infrared. The camera does not reveal a new object, so much as it reveals the same object in its native language. The first billion years also compresses time in a way that distorts intuition. At redshift 8 or 10, a difference of a few 100 million years is a large fraction of cosmic history. Small errors in redshift translate into large errors in inferred age. A misread spectral break can move a galaxy from impossibly early to merely surprisingly early, and the difference matters. It matters because star formation histories are steep there, and because enrichment can race ahead once the first supernovae begin. When the clock is that tight, every assumption about age becomes a lever. JWST changes the conversation by design. Its primary mirror is large enough to collect far more photons, and its instruments are tuned for near and mid-infrared, where redshifted starlight and nebular emission now live. It can detect rest frame ultraviolet starlight that has been stretched into infrared by expansion, and it can do it with stable, cold optics that keep the background low. That cold matters, because a warm telescope glows in infrared like a lantern in a dark room. JWST is engineered to be dim so that the universe can be bright. There is also a quieter advantage that rarely makes headlines. JWST's angular resolution in the near-infrared is sharp enough to separate compact sources that would blur together in older images. That separation reduces confusion, which is a technical word for a simple problem. When many faint things overlap, brightness becomes unreliable. In the early universe, where galaxies cluster and lensing can crowd fields, confusion can masquerade as discovery. A single bright dot can be a blend of several ordinary dots, and blends are persuasive liars. That sensitivity matters because early galaxies are compact and distant. Their light is diluted by distance, and then spread by the telescope's point spread function into a tiny, softened patch. JWST still sees them as small, but it sees them clearly enough to measure colours and spectra, and to notice when a galaxy is really two components pressed together. It can also detect the subtle colour differences that hint at strong emission lines hiding inside broad filters. Those differences are small on the detector, yet enormous in their implications. The visuals change with the data. Where Hubble showed a handful of faint smudges at the edge of detection, JWST reveals textured points, some with hints of structure, some with companions, some with elongated shapes that whisper of lensing. In deep fields, the sky becomes crowded with red dots and tiny arcs, each one a candidate from an era once treated like a blank space. The background is no longer empty black, but a layered tapestry of faint sources stacked through time. Even the noise looks different because the signal now has room to emerge. The result is a new discovery space. The first billion years move from sparse anecdotes to statistical samples, and that shift is more important than any single record breaker. Instead of asking whether one monster exists, we start asking how common monsters were, and whether the monstrous category itself needs revision. A sample forces us to define what we mean by normal, and it forces us to confront selection effects. When the map fills in, the coastline stops being a guess. Statistics change the emotional temperature of the debate. A lone outlier can be dismissed as a fluke, a measurement error, or a rare alignment. A population is harder to dismiss, because it demands a mechanism that operates repeatedly. JWST's early catalogues do not just add objects, they add pressure. They also add the possibility that our previous surveys were biased toward the rarest beacons, because only the loudest voices could be heard. Now we can listen to the crowd, not just the megaphones. The first wave of JWST results lands like a provocation, partly because the images are so clean, and partly because the candidates are so bright. Surveys report surprisingly luminous galaxies at redshifts once considered nearly unreachable for routine detection. Some candidates appear massive, structured, and chemically evolved earlier than expected, as if the universe began building cities while our models still expected villages. The provocation is not only brightness, but apparent maturity. Colours that hint at older stars and morphologies that hint at organised assembly. When the universe is supposed to be young, organisation feels like a contradiction. Brightness is the bait, but interpretation is the trap. A bright source at high redshift can mean high stellar mass, extreme star formation, or an accreting black hole dominating the energy budget. It can also mean dust, lensing magnification, or a photometric redshift mistake that quietly moves the object closer. The same handful of photons can support several stories. Those stories differ in physics, but they can look similar in a few broadband points. The danger is not that we guess wrong once, but that we build a narrative before the checks arrive. In the earliest announcements, the story often begins with photometry, because photometry is fast and it scales. A galaxy drops out in certain filters because intergalactic hydrogen absorbs short wavelengths, producing a sharp change in observed colour. That dropout pattern can mimic high redshift, but it can also be faked by dust and older stellar populations, especially when the signal to noise is modest. The method is powerful because it is simple, yet simplicity is also where degeneracies hide. A steep dust-reddening curve can imitate the same colour step we attribute to the Lyman break. The dropout method has a history that stretches back to the first deep Hubble fields. It was a triumph of inference, turning broad filters into a crude redshift ruler. Yet it was always vulnerable to imposters, and the imposters become more persuasive when galaxies are intrinsically red. JWST finds many red sources, and not all of them are ancient. Some are simply dusty, and some are dominated by emission lines that push flux into certain filters. The method still works, but it now operates in a more crowded and more deceptive landscape. Spectroscopy is the hard check. It looks for emission lines and continuum breaks that pin down redshift, replacing a probabilistic guess with a measured anchor. JWST can do this for sources that were previously too faint for reliable spectra, and it can do it across a wavelength range where key features land for very high redshift objects. The spectrum is not just a confirmation stamp because it carries chemical information. Line strengths and ratios can hint at metallicity, ionization, and the hardness of the radiation field. Even with spectra, the debate does not end because the early universe is a hostile place for clean diagnostics. A strong line can be Lyman alpha, but it can be suppressed by neutral hydrogen in the intergalactic medium. Other lines can shift in and out of band, and line ratios can be ambiguous in noisy data. Sometimes the spectrum offers a few peaks and a slope, and the rest is argument. The continuum can be faint, and the lines can sit on top of detector systematics that demand careful calibration. In that regime, certainty is earned slowly. This is where the mystery deepens rather than resolves. A clean redshift does not automatically yield a clean mass, because mass is not measured directly. Mass is inferred through models that translate light into stars, and those models were trained in a later universe. The first billion years may not follow the same rules. Even the meaning of stellar age shifts, because a galaxy can be dominated by a tiny fraction of very young stars. The light can be young while the mass is older, and the two are easy to confuse. So the early universe becomes a moving target. Headlines say too massive too early, then follow-up papers revise masses downward, sometimes dramatically. The revisions are not embarrassment. They are the normal process of turning first detections into physical models, and of discovering where the assumptions were doing more work than the data. Early fits often assume smooth star formation histories, because smoothness is computationally convenient. Yet the first galaxies may have formed in bursts, and bursts change the inferred mass-to-light ratio. The central issue is mass-to-light ratio, a deceptively simple phrase. If a galaxy is young and dominated by hot, massive stars, it can be bright per unit mass, like a fresh flame that outshines its fuel. If it is older or dustier, the same brightness implies more mass, because the light per kilogram of stars is lower. In practice, every inferred mass is a negotiated settlement between brightness and assumed stellar physics. That negotiation becomes tense when nebular emission adds light that is not from stars at all. A filter can be bright because gas is glowing, not because the stellar population is huge. Stellar population modelling is where assumptions hide. The inferred mass depends on the initial mass function, the star formation history, the metallicity, and the dust attenuation law. Change those inputs and the same colours yield different masses, because the model is a dictionary translating photons into populations. In the early universe, the dictionary may be incomplete. The IMF could be top-heavy, meaning more massive stars per unit total mass, which would make galaxies brighter without making them heavier. Even modest shifts in the IMF can move masses by factors that matter for the headline. Consider metallicity, which in astronomy means everything heavier than helium. Low metallicity changes stellar temperatures and lifetimes, often making stars hotter and bluer for the same mass. Hotter stars produce more ionizing photons, which then light up surrounding gas. That gas emits strong nebular lines that can flood broadband filters, making a galaxy look brighter and redder in ways that confuse simple fits. Oxygen and hydrogen lines can dominate bandpass, and a model that assumes weaker lines can mistakenly assign that flux to older stars. The result is an inflated mass, built from misplaced light. Dust complicates everything in both directions. Dust can dim ultraviolet light and redden colours, making a galaxy look older and more massive than it really is. Dust can also re-emit energy in infrared, making the total luminosity look extreme even when the starlight is partially hidden. In a JWST image, dust is both a veil and a lantern. The geometry matters too, because dust can be clumpy rather than uniform. A clumpy medium can let some ultraviolet escape while hiding other regions completely, creating colours that do not match simple screen models. The early universe adds another twist. Dust itself must be made. Dust grains form in the envelopes of evolved stars and in supernova ejecta, processes that require time and previous generations of stars. So when a very high redshift galaxy appears dusty, it raises a question about speed. How quickly did the first stars enrich their surroundings, and how efficiently did that enrichment become obscuring grains? It also raises a survival question, because shocks can destroy dust as easily as they create it. A dusty early galaxy implies not only production, but retention. Then there is the starburst versus AGN question, which is not just taxonomy. A compact starburst can produce intense ultraviolet light and strong nebular lines, especially when gas densities are high. An accreting black hole can produce a hard ionizing spectrum, hot dust emission, and broad lines when the central region is visible. Both can be bright, compact, and red. Both can also coexist in the same galaxy, sharing a gas reservoir and competing for it. When we classify, we're often forcing a continuum into two bins. JWST is finding candidate active nuclei at high redshift. Some sources show line widths, ionization states, or mid-infrared excesses consistent with accretion, and some show spectral energy distributions that resist purely stellar explanations. Others remain ambiguous, because extreme star formation can mimic parts of the signature, and because dust can reshape the spectrum into misleading forms. The ambiguity is sharpened by limited spatial resolution at those distances. A nucleus and a starburst can be separated by hundreds of parsecs, yet still blur into one point. In visuals, the ambiguity is almost poetic. A tiny point of light sits in a field of darkness, and the data reduce it to a few coloured dots and a jagged spectrum. From that, we try to decide whether the engine is millions of stars or a single black hole. We're reading a distant furnace through a keyhole. The spectrum becomes a kind of fingerprint, but the fingerprint is smudged by noise and by the intervening universe. We squint at the ridges, and we argue about the match. This ambiguity is not a side detail. It is the same ambiguity that haunts TON 618 in a different form, because we are always inferring an engine from light we cannot spatially resolve. We cannot watch gas spiral into a horizon at redshift 10. We see the glow of the disk, the reprocessed light of dust, and the fingerprints of ionized gas. We also see variability only in slow motion, because the light travel time and the faintness limit what we can monitor. The engine is real, but our access is indirect. When a source is brighter than expected, we reach for the simplest explanation. We say it is more massive, or it formed earlier, or it is forming stars faster than anything nearby. But the early universe is not obligated to match local calibrations, and local calibrations are the scaffolding behind many quick interpretations. Those calibrations were built from galaxies with long histories of enrichment and feedback. They were built in an era when the cosmic microwave background was colder and the universe was less dense. Local calibrations assume mature metallicities and familiar dust. They assume star formation proceeds with an IMF similar to today's, with a stable ratio of massive to low-mass stars. They assume AGN templates built from lower redshift samples, where galaxies have had time to settle into regulated cycles. Those assumptions are practical, but they are not guaranteed. They are also seductive because they let us translate light into numbers quickly. Yet quick translation can hide systematic errors that only appear when the sample grows. In the first billion years, those assumptions may break. Low metallicity changes stellar spectra, which changes the colours used to infer ages. Nebular emission lines can dominate broadband flux and inflate inferred stellar masses because the model mistakes line light for continuum. Even the geometry of dust can differ, making attenuation laws less like a smooth screen and more like a patchwork. The interstellar medium itself can be more porous, carved by supernovae and radiation pressure. A porous medium changes escape fractions, which changes the observed ultraviolet brightness. This is one reason some too massive too early claims soften over time. Once strong line contamination is modelled, the stellar continuum can be lower than first assumed. The galaxy can be less massive while still being unusually bright, because the brightness was partly gas emission rather than starlight. The monster shrinks, but the crowd remains, and the crowd is the more important result, because it shifts the question from exception to environment. If many objects look bright, then the early universe is doing something consistently. Yet the pattern does not disappear. Even after careful modelling, JWST still finds many luminous sources at high redshift, and the luminosity function appears elevated in ways that keep theorists uneasy. The early universe looks more productive than we expected, even if the most extreme numbers are revised. The question becomes whether productivity is a measurement artifact or a physical clue. Productivity can mean higher star formation efficiency, less dust attenuation than assumed, or a burstier duty cycle that makes galaxies flare bright. It can also mean that we are catching them at a special moment, because selection favours the loudest phases. That productivity matters for black hole growth. Massive galaxies imply deep potential wells and abundant gas reservoirs, and both are friendly to sustained accretion. Deep wells make it easier to retain gas against feedback, and abundant gas makes it easier to feed a nucleus without immediately starving it. If galaxies assemble quickly, black holes may find themselves in richer kitchens. The same inflows that build a bulge can also build a black hole, if angular momentum can be shed. The question is whether the inflow reaches the centre, or stalls in a star-forming ring. The black hole seed problem returns with new urgency. If luminous AGN exist at very high redshift, then seeds must form early and grow fast, because the cosmic clock is unforgiving. The same exponential clock from Chapter 4 is still ticking, and every misty folding is a lost opportunity. When the universe is young, delays are expensive. Even 100 million years can be the difference between a modest black hole and a quasar. The arithmetic does not care about our discomfort. Stellar remnant seeds struggle because they start too small. They require near-continuous accretion at high duty cycle, and they must do it while surrounded by violent star formation. They must also survive kicks from asymmetric supernovae and gravitational interactions, and they must navigate the chaos of early mergers. A seed that is thrown out of its halo is a seed that stops growing. Even if it stays, it can be starved by feedback from nearby massive stars. The environment that makes many stars can also make black hole feeding difficult, so attention shifts to heavy seeds. Direct collapse black holes become more than a niche idea, because they offer a head start that the clock seems to demand. They offer starting masses of 10,000 to 1,000,000 suns, which shortens the growth path by orders of magnitude. A heavy seed does not solve everything, but it makes the arithmetic less cruel. It also changes what early means, because a heavy seed can become a quasar without needing a perfect accretion history. The burden shifts from constant feeding to plausible feeding. Direct collapse requires special conditions. Gas must avoid fragmenting into normal stars, because fragmentation turns a collapsing cloud into a cluster instead of a single central object. Molecular hydrogen cooling must be suppressed, often by a strong Lyman or an irradiation background that dissociates H2. Without H2, the gas stays warmer, and warm gas resists breaking into many small pieces. The collapse then proceeds in a more monolithic way, with inflow rates that can be enormous by stellar standards. The temperature floor is higher, yet the central density can still rise fast. That background implies a neighbourhood with intense star formation. It must be close enough to dissociate H2, yet not so close that metals and dust pollute the collapsing cloud and enable efficient cooling. The niche is narrow, and it sounds like fine-tuning when described in isolation. JWST-era statistics ask whether the early universe produced that niche often enough to matter. Fine-tuning is less troubling if the universe offers many trials. A crowded early cosmos can run the experiment repeatedly across many halos. We can picture the geometry. A pristine gas halo sits near a bright, young galaxy that floods space with ultraviolet photons. The radiation keeps molecules from forming, while gravity keeps pulling gas inward. Too close, and the halo is enriched and fragmented. Too far, and molecules form and stars ignite. Somewhere in between, the conditions may allow a direct plunge. Visually, it is a delicate balance drawn in light and shadow, an illuminated neighbour, and a darker halo trying to stay chemically untouched. The window is small, but the stakes are large. Super Eddington episodes also return to the centre of the discussion. Thick disks can trap radiation and allow higher inflow rates, because photons scatter and diffuse rather than pushing matter away efficiently. Funnel geometries can let light escape along polar directions while mass continues inward in the equatorial plane. The system can look extremely luminous while still swallowing more than the classical limit suggests. In that regime, the Eddington limit is not a wall, but a guideline that depends on geometry and opacity. The early universe may provide the dense gas needed to sustain such states. The key question is duration and repetition. A short super Eddington burst helps, but it does not solve a multi-100-million-year growth requirement by itself. The early universe must provide sustained inflow without permanent self-starvation, and it must do so while feedback is actively trying to shut the process down. Growth is not just a rate, it is a balance. It is a balance between gravity pulling in, radiation pushing out, and the messy physics of turbulence redistributing angular momentum. The engine must keep its fuel line open while it is actively heating the room. Environmental factors may provide that inflow. Primordial halos are denser on average at high redshift, because the universe itself is denser and structures are more compact. Cooling times are shorter in dense gas, and dynamical times are shorter in compact systems, meaning gas can respond quickly to gravity. What takes 1 billion years later can happen in a few 100 million earlier. The potential wells are smaller, yet the inflows can be more intense because the cosmic web is feeding them rapidly. The early universe is not calm, but it is efficient. Low metallicity changes cooling pathways in ways that cut both directions. Without metals, gas can stay warmer and resist fragmentation, which can reduce star formation efficiency in some regimes. Less fragmentation can leave more gas available for central inflow, which is helpful for seeds. Yet warm gas also means higher pressure, and pressure can delay collapse unless gravity wins decisively. The outcome depends on density, turbulence, and radiation fields, which vary from halo to halo. In other words, the early universe is a factory with inconsistent settings. At the same time, atomic cooling halos at around 10,000 Kelvin can drive rapid collapse once they cross a mass threshold. Hydrogen line cooling becomes effective, and gas can lose energy fast enough to fall inward. If angular momentum can be redistributed through turbulence bars or instabilities, gas can pile up in the center. The difference between a starburst and a seed may be a small shift in turbulence and radiation. A slight change in inflow coherence can decide whether gas settles into a disk that forms stars or plunges into a dense central object. Cosmic filaments matter more in this era. Cold streams can penetrate halos and deliver gas directly to central regions, because shocks are less effective at heating everything to the virial temperature. The inflow can be coherent, fast and continuous compared to later epochs, when hot halos and feedback often disrupt the supply. In the early universe, the plumbing is more direct. The streams can also carry low metallicity gas, which keeps cooling behavior in the primordial regime. That matters because the chemical state of the inflow shapes what happens at the center. Visually, those filaments are the hidden architecture behind the bright points. Simulations show them as faint, glowing threads feeding nodes, like rivers converging on a dark lake. JWST does not image the filaments directly in most cases, but the galaxies it sees are likely sitting at the nodes. The crowd is not random, it is shaped by the web. When we look at a deep field, we're seeing the bright intersections, not the faint scaffolding between them. The unseen structure is doing much of the work. Merger rates are also higher. Small halos collide frequently as the cosmic web assembles, and each collision can torque gas and drive instabilities. Mergers can trigger starbursts by compressing gas, and they can also funnel gas toward a central nucleus by removing angular momentum. In an early gas-rich universe, mergers are not rare interruptions, they are a lifestyle. The remnants can be messy, with clumps and tidal features that blur into compact shapes at great distance. Yet the dynamical consequences can be profound, because torque is an efficient way to feed a center. These are not separate stories. They are coupled feedback loops, and the coupling is where nonlinear behavior emerges. Mergers feed star formation. Star formation builds radiation backgrounds. Radiation backgrounds shape cooling, and cooling determines whether gas fragments or collapses. A small difference in environment can cascade into a large difference in outcome. That cascade is why rare extremes can exist without violating average behavior. The mean can be modest while the tail becomes heavy. JWST is forcing us to confront how nonlinear early structure formation may be. A small change in initial conditions can produce a rare node that grows far ahead of the mean simply because it sits at a privileged intersection of filaments. Those rare nodes are exactly where monsters would form, and their rarity does not make them irrelevant. Rare objects can dominate the narrative when they expose the limits of our rules. They also test our simulations, because tails are where numerical resolution and subgrid physics matter most. If the tail is wrong, the rulebook may be incomplete. This is where TON 618 re-enters as an emblem rather than an outlier. It is not just a single quasar with a large inferred mass. It is a sign that the tail of the distribution may be heavier than our models allow, and that the early universe may have been better at building extremes than our intuition admits. TON 618 becomes a reminder that our comfort depends on scarcity. When scarcity fades, comfort fades with it. Even if some JWST claims are revised, the tension escalates. We already knew about billion solar mass black holes at very high redshift from pre-JWST surveys, and those objects were already uncomfortable. JWST adds more candidates and more context, which makes the discomfort harder to localize. The problem stops being one quasar and becomes an ecosystem. An ecosystem implies not just isolated miracles but repeated pathways. It implies that whatever builds a quasar can be a common phase, not a cosmic accident. The context is that galaxies themselves may assemble faster. If galaxies are forming early and bright, then the fuel and scaffolding for black holes are also early. That helps, but it also raises the bar for feedback and regulation, because fast assembly can trigger fast self-destruction if energy output is too strong. A galaxy that grows quickly must also manage its own heat. It must keep gas cool enough to continue forming stars and feeding a nucleus, while surviving the winds and radiation those processes generate. The balance is precarious, and that precariousness can produce bursts. A universe that builds structure quickly is a universe that can build extreme structure quickly. The question becomes whether our growth limits are too strict, or whether our interpretations of light are still incomplete, or both. When a model fails, the failure can be in the physics or in the translation from photons to parameters. The translation is where we are most vulnerable, because it is built from templates. Templates are useful, but they are also historical artifacts. Some of the apparent crisis may be bookkeeping. Photometric redshifts can be wrong, especially when spectral breaks are confused with dust reddening. Stellar masses can be inflated by line contamination. especially when strong oxygen or hydrogen lines land in broadband filters. Dust laws can shift inferred ages and masses because attenuation curves are not universal. Even lensing can quietly amplify brightness, because a modest magnification can push an object into a sample. When the sample is defined by brightness, magnification matters, but not all of it is bookkeeping. Spectroscopically confirmed luminous sources at high redshift are real, and their existence is not negotiable. Some show signatures that are difficult to explain without accretion, even when generous starburst models are allowed. The early universe contains engines that look, at minimum, suspiciously like quasars. That suspicion is not based on one line, but on a pattern of ionization and continuum shape. The data are still young, yet the direction is clear. The debate shifts from existence to mechanism. If early AGN are common, then seed formation must be efficient, because many seeds must appear quickly. If early AGN are rare but extremely luminous, then growth must be episodic and extreme, with bursts that carry much of the mass gain. Either path points to a rulebook problem, because the local universe trained our intuition on regulated systems. Regulation is an emergent property of maturity, and the early universe may not have matured yet. It may have been willing to overshoot, then crash, then rebuild. The local universe teaches a kind of moderation. Black holes correlate with bulge properties, and feedback appears to limit runaway growth, at least on average. Gas fractions are lower, metallicities are higher, and disks are more settled. The early universe may have been less regulated, more gas-rich, and more willing to run away, because the supply was abundant and the structures were still forming. Even the background radiation field was different, because the cosmic microwave background was warmer. A warmer background can affect how cold dust and gas can become, which subtly shifts the thermal balance. This is why the phrase "something worse" belongs here. The worst thing is not a single object breaking a timeline, because outliers can always be argued away. The worst thing is a pattern suggesting the timeline itself is incomplete, and that our supposed limits were calibrated in the wrong era. If the early universe plays by different rules, then the limits are not limits. They are local habits mistaken for universal laws. Ton 6-18's light left when the universe was younger than it is now by more than 10 billion years. JWST is now filling in the surrounding era with a menagerie of bright, compact systems, some starbursting and some possibly accreting. The monster is no longer alone in the dark, and loneliness was part of what made it feel dismissible. When you see one extreme, you can call it luck. When you see many, you have to call it physics. We can try to domesticate each new result. We can lower a mass estimate, change a dust model, or reclassify a source as starburst dominated rather than AGN dominated. Those moves are often justified, and they are part of honest science. Yet the overall census keeps pointing toward early efficiency, as if the universe learned to build quickly before it learned to build neatly. The messiness may not be a bug, but a feature of rapid assembly. A hurried universe leaves fingerprints in its spectra. Efficiency in building stars and galaxies implies efficiency in building black holes, unless some strong decoupling exists. Yet black holes and galaxies are coupled by gravity, and by shared gas reservoirs, and that coupling is why feedback matters. When gas falls inward, it feeds both star formation and accretion. Then the resulting energy pushes back on the same reservoir. The pushback can be radiative, mechanical, or both, and the coupling depends on geometry. A narrow jet can punch through, while a wide wind can sweep a galaxy. The same luminosity can have different consequences depending on how it is delivered, so the question sharpens again. What is Ton 6018 really if it sits on top of a broader early universe trend, rather than standing alone as a freak event? Is it an extreme case of ordinary accretion, amplified by favourable conditions and long duty cycles? Or is it evidence that seeds and inflows can be far more violent than our conservative models allow? The word violent is not rhetorical, because the energies involved are enormous. A growing black hole can outshine its host, and that light can reshape gas on galactic scales. The opening hook returns as a constraint, not a metaphor. 10 billion years ago, something violent happened around a monster, and the aftermath still reaches us as a measured spectrum. JWST suggests the early universe hosted many violent engines, even if most were smaller and shorter lived. If so, violence was not an exception. It was a developmental stage. A young universe may have grown the way young organisms grow, fast, uneven, and sometimes wasteful. The waste in this case is energy poured into space, If that is true, then the message arriving now is not one signal. It is a chorus of signals, each red-shifted into infrared, each carrying a record of rapid assembly and intense radiation. The sky becomes an archive of runaway growth, and the archive is suddenly legible. We are no longer guessing at the first chapter from a single surviving page. We are reading multiple pages at once and comparing handwriting. This chapter is not a verdict on every JWST headline. It is a shift in stakes, because the early universe is no longer a blank page where simulations can write anything plausible. Now the page has ink, and the ink has error bars, spectra, and repeat detections across fields. Repeat detections matter because they reduce the chance of a single field being unusual. They also let us test cosmic variance, which is another way the universe can mislead. A small patch of sky can be a special neighbourhood, and JWST is now sampling more neighbourhoods. Bright galaxies appear where models expected dim ones. Candidate nuclei appear where seeds were supposed to still be small, and where accretion was supposed to be limited by feedback. The first billion years look crowded, and crowding accelerates everything, because interactions become common, and gas flows become turbulent. Turbulence is not just disorder, because it can transport angular momentum. Transport is what turns a reservoir into a fuel line. That acceleration does not automatically solve TON 618. It can supply more fuel, more mergers, and more dense environments, and those are the ingredients growth models crave. But it also demands that feedback and radiative limits be re-evaluated under primordial conditions, where metallicity, dust, and geometry differ. A limit derived from mature galaxies may not apply to newborn ones. Even the opacity of the inflowing gas can differ, which changes how radiation couples to matter. If coupling is weaker, then the same luminosity pushes less effectively. The rulebook problem deepens because it is now multi-scale. It's about how halos assemble, how gas cools, how stars form, and how black holes feed, and each scale hands boundary conditions to the next. A mismatch at any stage can echo into the mass function we observe, making the final discrepancy hard to localize. This is why debates can sound circular, because each explanation shifts the burden to another scale. Fix the stellar models, and the halo growth becomes the issue. Fix the halo growth, and the accretion physics becomes the issue. So we end with a deliberate narrowing of focus. If the early universe can build monsters quickly, then the engine physics matters more than ever, because engines are where limits are enforced or broken. We need to understand what a quasar does to its surroundings while it grows, and what its surroundings do in return. We need to know how radiation heats gas, how winds carve channels, and how inflows survive in the presence of that violence. We also need to ask a harder question. When does feedback regulate, and when does it merely rearrange the fuel? To understand the something worse, we zoom into the engine room. We follow energy from the disk into winds, jets, and radiation fields, and we track how that energy couples to gas at different distances. We ask how a quasar reshapes space-time, matter, and the galaxies trying to form around it, because the answer decides whether monsters are rare accidents or a natural outcome. We zoom into the engine room because the growth problem becomes physical here, and because physics is easiest to respect when it has teeth. TON 618 is not just a mass estimate on a plot. It is a region where space-time, plasma, and light negotiate a brutal balance, one that can be stable for years, then fail in minutes. The camera drifts through an imagined darkness, then catches the first hints of structure. A flattened glow appears, not as a solid object, but as a whirlpool of incandescent gas. The brightness is not uniform because motion and gravity paint it into gradients. Even the emptiness looks textured here, as if the void has been stretched into threads. At this scale, the word edge misleads, because our instincts expect a surface. A black hole has no surface to crash into, no crust to strike, and no last wall. The boundary is a one-way geometry where paths that point inward cannot point back. It is less like a cliff, and more like a rule built into the map. In general relativity, that rule is not a force in the usual sense. It is a reshaping of what counts as a possible future. Outside the horizon, light cones still leave options open. Inside, every future-directed path points deeper inward. So, escape stops being a direction you can choose. Near the horizon, gravity is not simply stronger, because strength alone is a blunt description. It is steeper, and the steepness matters more than the number. Tidal forces measure that steepness because they compare gravity here to gravity a meter away. They stretch objects along the radial direction and compress them sideways as if space itself is kneading matter. A vivid way to picture it is to imagine a long object falling feet first. The feet feel a larger pull than the head, and the difference grows as the object descends. That difference is what turns a fall into a tearing. For stellar mass black holes, the tearing can happen well outside the horizon. For a supermassive object, the horizon itself can be gentle in local terms, at least for something small compared to the whole. The gradient at the boundary can be mild enough that an astronaut would not be spaghettified at the crossing. Yet the environment is not gentle, because the disk sits deeper than the safe orbit, and because radiation saturates the region. The danger is not the horizon alone. The danger is the plunge region and the radiation field. Stable orbits end at the innermost stable circular orbit, and inside it motion becomes a fall. The ISCO is not just a location, but a threshold in the orbital energy landscape. Outside it, small perturbations can settle into another orbit. Inside it, there is no stable compromise, only a spiral that tightens into a plunge. Gas can still orbit briefly, because inertia does not vanish at a boundary, but it is losing the argument with curvature and with its own internal stresses. The last turns are fast, hot, and short, and they happen while matter is still luminous. In those final orbits, orbital speeds become a significant fraction of light speed. The camera would see the disk's inner rim blur into a ring of motion. Bright patches shear into arcs, then smear into a near-continuous band. Magnetic loops rise and reconnect above the surface, flashing like heat lightning. The light is not calm because the flow is not calm. Light itself has preferred paths here, and that is one of the strangest reveals. There are photon orbits where gravity can bend light into loops. Those loops are unstable, so a tiny nudge sends a photon outward or inward. The orbit is like a knife edge, balanced for an instant, then lost. The result is a lens made of space-time, not glass. It can brighten some regions and dim others depending on viewing angle. It can also create multiple images of the same patch of disk, layered like reflections that do not quite align. Even when we cannot resolve the structure directly, the lens leaves fingerprints in the spectrum and variability. If we could hover above the disk, we would see the far side lifted into view. The underside would appear as a warped ribbon because light rays bend around the hole. The black region in the center would not be a simple circle. It would be a shadow shaped by photon capture and by the geometry of emission. Time behaves like a gradient, and the gradient is measurable in principle. Clocks deeper in the potential run slower relative to distant observers. Variability from the inner disk is stretched by gravitational time dilation and by cosmic redshift. What happens in seconds near the engine can arrive as minutes in our data. That stretching is not merely poetic, because it changes how we interpret flicker. A flare that seems leisurely from Earth may be frantic at the source. When astronomers use variability to infer size, they are implicitly using causality as a ruler. The fastest changes imply the smallest emitting regions, even when the regions are moving. Color behaves like a gradient too, and the shift is not subtle near the horizon. Photons climbing out lose energy and shift to longer wavelengths. Gravitational redshift stacks on top of Doppler shifts from orbital motion. The same gas can look bluer on one side and redder on the other, even if its temperature is uniform. Doppler beaming makes the approaching side of the disk brighter, because light is concentrated in the forward direction of motion. The receding side is dimmer and redder because photons are spread out and lose energy. Even without resolving the disk, the spectrum carries this asymmetry. It is a hidden map, encoded in line shapes and continuum slopes. Spin adds another layer of complication, because it drags spacetime itself. In a rotating black hole, the region outside the horizon is not static. Frame dragging twists the inertial frames, and it can pull orbits inward. A faster spin moves the ISCO closer, allowing more gravitational energy to be released as radiation. That is why the same mass can power different brightness levels. The engine is not only how much matter you have, but how deep you can tap the potential. Spin changes the depth of the well. It also changes the geometry of magnetic fields near the center, which matters for jets. This is where the investigative tone sharpens, because the constraints stack rather than cancel. The same physics that makes the quasar bright also makes the feeding difficult. The same gravity that traps light also powers the light. Every solution to luminosity becomes a new question about supply. The accretion disk is the actual power plant we observe, and it is more like a refinery than a campfire. Gas falls in with angular momentum, so it cannot drop straight down. It forms a rotating disk that must shed angular momentum to move inward. Without that shedding, the gas would simply orbit forever. Bright perhaps, but not growing the central mass. The disk is thin in some regimes and thick in others, but it is never simple. It is stratified by temperature, density, and ionization. The midplane can be dense and opaque, while the surface layers are hotter and more rarefied. Radiation escapes from a photosphere that is not a hard boundary, but a depth where photons finally decouple. The key mechanism is turbulence driven by magnetic fields because ordinary viscosity is far too weak. Magnetorotational instability turns weak fields into strong stresses. It exploits a basic fact: inner orbits move faster than outer orbits. A magnetic field line linking the two acts like a spring, transferring angular momentum outward. That transfers the disk's hidden machinery. The inner gas loses angular momentum and sinks, while the outer gas gains it and moves outward slightly. The process is messy and time-dependent, producing eddies, reconnection events, and intermittent heating. In simulations, the disk looks alive, full of braided field lines and churning cells. Heat is the intermediate currency, and it is generated whether we want it or not. The disk radiates because it must get rid of energy to keep spiraling inward. The radiation is not a byproduct. It is the price of losing angular momentum. If the disk could not radiate, it would puff up, stall, and change its own rules. In the inner regions, temperatures rise high enough to emit ultraviolet and soft X-rays, because the gravitational energy release per kilogram is enormous. Farther out, the disk cools and shifts toward optical and infrared. The spectrum is a layered map of radius, like tree rings that record conditions at different distances. When we decompose the light, we are effectively reading the disk's temperature profile. The ultraviolet is especially important because it ionizes surrounding gas and powers emission lines. The soft X-rays hint at a hotter component and at Compton scattering. The infrared tells us where dust intercepts and reprocesses the energy. Even when the central engine is hidden, the reprocessed light can betray its presence. Quasars are efficient because gravity is efficient, and because the conversion happens in a deep potential well. Fusion converts less than 1% of rest mass into energy. Accretion can convert several percent to tens of percent depending on spin. In the most favourable cases, a significant fraction of the infalling mass is turned into light and outflow power. That efficiency is why a quasar can outshine a galaxy, even though it occupies a region smaller than the solar system in some cases. It is also why growth is constrained by feedback, because brightness is not passive. If too much energy escapes as light, it pushes on the same gas trying to fall in. The engine can choke on its own success. The Eddington idea returns here as a force balance, not a slogan. Photons scatter off electrons and transfer momentum outward. Gravity pulls inward mainly on protons, but the plasma stays coupled through electric forces. The electrons cannot leave without dragging ions along, so the whole gas responds. A luminous disk can therefore regulate its own fuel supply, at least in idealized conditions. If the flow is thin and roughly spherical in its coupling, radiation pressure can halt inflow. The quasar becomes self-limiting, hovering near a characteristic luminosity for a given mass. That limit is not a law of nature so much as a common outcome of competing forces. Yet TON 618 exists, which means the limiting is not absolute. Geometry can bend the rules without breaking them. Thick disks can trap photons, and trapped photons push less effectively outward. When photons are repeatedly scattered and carried inward with the flow, they do not deliver their momentum to the gas that is still trying to fall. In a thick flow, energy can be advected inward faster than it diffuses outward, and that changes what brightness means locally. Radiation escapes through funnels and lower density channels. The system can exceed naive Eddington inflow while looking only modestly super Eddington. The quasar can be swallowing more than its light suggests. The visuals here would shift from a flat disk to a swollen torus-like structure. A bright funnel opens along the axis, like a searchlight carved through fog. Photons ricochet inside the dense gas, then finally leak out where the path is shortest. The disk becomes a three-dimensional object, not a record on a turntable. Magnetic fields complicate the story again, because they do not only transport angular momentum, they can also extract rotational energy and collimate outflows. The disk is not a flat lamp, It is a magnetized machine. In some regimes, the magnetic pressure can rival the gas pressure, altering thickness and stability. Above the disk, a hot corona can form, and its origin is still debated in detail. It may be powered by magnetic reconnection, by buoyant field loops, or by dissipation in a tenuous atmosphere. In any case, the corona can upscatter photons to X-ray energies through inverse Compton processes. Those X-rays are a diagnostic because they probe the hottest, most compact regions. Those X-rays ionize surrounding gas and change its opacity, and opacity is the lever arm of radiation pressure. Ionized gas has fewer bound electrons to absorb line radiation, which can weaken line-driven winds, but it also changes electron scattering and thermal balance, which can strengthen other kinds of outflow. Feedback is not one loop, but several loops braided together. Around the disk sits the broad line region, where fast clouds or streams reprocess the continuum. Their emission lines are Doppler broadened by thousands of kilometers per second. Those widths are one anchor for the mass inference, because they encode orbital speed. The method assumes the gas is gravitationally bound and roughly virialized, even if the geometry is complex. The broad lines also carry chemical information. They reveal heavy elements that must have been forged in earlier generations of stars. That fact matters, because it tells us the host galaxy had already undergone rapid enrichment. The quasar is not forming in pristine darkness. It is forming in a young universe that is already chemically busy. Farther out, dust can survive and re-radiate in infrared, but only beyond a sublimation radius set by the quasar's glare. That dusty region is not a wall. It is a distribution shaped by illumination, winds, and clumpiness. In some directions it hides the nucleus, while in others it leaves a line of sight open. So when we say we see TON 618, we mean we see this structure, layered and indirect. We see continuum from hot gas, lines from ionized gas, and thermal emission from dust. We see absorption features where intervening material bites into the spectrum. The central object remains dark, not because it is absent, but because it is defined by what it does not emit. The near-horizon region is therefore a paradox in practice. It is the most important region, and the least directly visible. The horizon is defined by what cannot send signals back. Our evidence is everything just outside it: matter heating, light bending, and time stretching. We're studying the boundary by studying the glow that fails to cross it. Historically, this is a strange place for science to have arrived. Dark stars were once a speculative idea, and black holes were treated as mathematical curiosities. The language of horizons and singularities matured slowly, through decades of theory and argument. Only in the quasar era did the universe force the issue, by presenting objects too luminous to be explained otherwise. When quasars were discovered in the mid-20th century, their redshifts implied staggering distances and energies. The debate was not only what they were, but whether the distances were real. Once the distances held, the engine had to be compact and efficient. Accretion onto supermassive black holes became the simplest answer, and it has survived because it keeps predicting what we see. Now the story widens from the disk to the galaxy, because the disk does not radiate into empty space. It radiates into gas that can be pushed, heated, and rearranged. The quasar is embedded in a host that is still assembling, still merging, and still drawing in cold material along cosmic filaments. The engine is local, but the consequences are not. Jets are the most dramatic channel for that energy, because they look like intent. They are narrow, relativistic outflows launched along the rotation axis. They require ordered magnetic fields and a rotating engine. In images and simulations, they resemble twin spears of plasma and field, drilling through surrounding gas. One pathway is disk-driven, where magnetic fields anchored in the disk fling plasma outward. Another pathway taps black holes spin through magnetic flux, threading the horizon, converting rotational energy into pointing flux. In both cases, the outflow is electromagnetic first and matter second. The jet begins as a structured field, then loads particles as it propagates. Relativistic speed changes what energy means, because kinetic energy scales steeply as velocity approaches light speed. A jet carries kinetic energy, magnetic energy, and momentum far from the nucleus. It can deposit that energy in the host galaxy and beyond, sometimes in hotspots where the jet terminates. The deposition is not gentle, because shocks and turbulence are part of the delivery. The visuals would pull back to show the jet carving a channel. The surrounding medium glows where it is shocked, and cavities open like wounds in the halo gas. Along the jet, knots brighten and fade, suggesting internal shocks or magnetic instabilities. The jet is narrow, but its influence can be wide. Winds are the wider cousin of jets, and they are often harder to see directly. They can be launched by radiation pressure on lines, by thermal pressure from X-ray heating, or by magnetocentrifugal forces. They are slower than jets, but broader, and often more massive. A wind can carry more total mass even if it carries less speed. Spectra reveal winds through blue-shifted absorption and asymmetric emission lines, and the details matter. A blue shift tells us gas is moving toward us along the line of sight. The depth and width tell us about column density and velocity spread. The lines become a weather report for the nucleus, tracking storms of ionized material. They tell us the quasar is not only shining, it is blowing. The outflow can be episodic, with bursts tied to changes in accretion state. It can also be stratified, with different ions tracing different temperatures and distances. In some cases, multiple absorption systems reveal multiple shells or streams. The impact on star formation is not one-directional, and that ambiguity is part of the mystery. Outflows can quench by removing gas and raising turbulence. Outflows can also trigger by compressing gas into dense shells. The same energy source can act like a fire that sterilizes one region while lighting another. Quenching is easier to picture because it is subtraction, and subtraction is visually clean. Heat the gas and it resists collapse. Remove the gas and stars cannot form. A quasar can therefore regulate the growth of its own host, not by destroying stars, but by changing whether new ones can be born. Triggering is subtler but real in some environments, especially where gas is already near instability. A shock front can compress a cloud past the threshold for collapse. The same outflow that empties one region can ignite another, like a blast wave that seeds new sparks. The result can be ring-like star formation, or localized bursts along compressed fronts. Either way, the quasar is a galaxy-scale actor, not a decorative nucleus. It changes the pressure balance, the ionization state, and the cooling efficiency of gas. It can reshape where the next generation of stars can form. It can also influence how gas flows inward, because turbulence and heating alter angular momentum transport on larger scales. The influence extends into the circumgalactic medium, the reservoir around a galaxy that acts as both pantry and wastebasket. Winds can carry metals outward, enriching gas that started nearly pristine. Enrichment changes cooling, and cooling changes future structure. A metal-enriched halo radiates energy differently, and that affects how easily it can condense back onto the galaxy. Jets can punch into the halo and inflate cavities, and those cavities can persist as buoyant bubbles. They can heat diffuse gas and prevent it from condensing, which is one route to long-term quenching. They can also stir magnetic fields and seed turbulence on large scales. The halo becomes a stirred atmosphere rather than a quiet reservoir. Beyond the halo lies the intergalactic medium, the web between galaxies that carries most of the baryons. Quasar radiation can ionize hydrogen over enormous volumes, and the effect propagates at light speed. That ionization changes how the IgM absorbs light from other sources. It also changes how the gas cools and collapses, subtly influencing later structure. So TON 618 is not only a bright point on a map, it is a transformer that converts gravitational potential into radiation and mechanical work. Its output becomes boundary conditions for its entire neighborhood. The quasar is an engine, but it is also an environment maker. This is why the chapter title matters, because mouth implies both intake and consequence. The mouth of space is not a metaphor for hunger alone. It is a description of a region that swallows matter and spits energy back out. The swallowing is silent, but the spitting is luminous, and the surrounding universe has to live with it. Now we pivot into the provocation that frames the film. TON 618 is called a black hole, yet we never observe the hole itself. We observe the consequences that match the black hole model. The object is defined by an absence of return signals, which means direct confirmation is structurally denied. We infer the central mass from velocities, luminosity, and size constraints, and each step has assumptions. Broad line widths give a speed scale, because faster gas produces broader lines. Empirical relations give a radius scale, linking luminosity to the size of the broadline region. The combination yields a virial mass with known scatter, and the scatter matters more at the extremes. Reverberation mapping is the gold standard behind those relations, even when it cannot be applied directly. In reverberation, the continuum varies first, then the lines respond after a delay. The delay gives a light travel size, like sonar made of photons. For the most distant quasars, we often rely on calibrations built from closer ones. We check that inference against other clues, because no single method is trusted alone. The luminosity cannot be powered by stars without violating energy budgets and size constraints. The variability implies a compact region, because a large region cannot change quickly without violating causality. The multi-wavelength spectrum matches accretion physics, from thermal disk emission to X-ray components. We also check for imposters, because the universe likes to cheat our measurements. Strong lensing could magnify brightness and distort inference, but there is no clear lensing signature in the images or spectra. A blazer-like alignment could boost flux through beaming, but the spectral properties do not demand extreme beaming. The object looks like a quasar, not a jet pointed directly at us. So the black hole is an inference anchored by consistent evidence. It is not a guess made from one line. It is a converging solution to multiple constraints, each imperfect but mutually reinforcing. The confidence comes from overlap, not from certainty. Still, the phrase "not a black hole" points to a real epistemic gap, and the gap is not a failure of effort. A horizon is defined by causal disconnection, which means it cannot be directly seen. We can image shadows and rings, but even those are light paths outside the boundary. The central darkness is a silhouette cast by gravity, not a photograph of an object. What we call a black hole is therefore a model of what must be there, given the external behaviour. It is a compact object with a deep potential, an event horizon, and predictable space-time effects. The model has passed many tests, from stellar orbits to gravitational waves. Yet the core remains hidden by definition, and that hiddenness keeps the door open to questions. That gap is where discomfort grows. If the universe can assemble something this massive so early, then our growth channels might include rare runaway processes. The worst thing is not a monster breaking one rule. It is a cosmos that can repeatedly find loopholes, and do it often enough to leave fossils in the sky. Runaway can mean a privileged environment in the cosmic web, where supply is not intermittent. Multiple filaments can feed a node with sustained inflow. High gas fractions can keep the nucleus supplied despite feedback. In a young universe, galaxies are denser and mergers are more frequent, which can funnel gas inward. Runaway can also mean phases we rarely catch, because visibility depends on orientation and obscuration. The fastest growth may be hidden by dust and gas, visible only in infrared or through indirect signatures. By the time the quasar is optically bright, much of the mass may already be gained. What we call ignition may be the late stage of a longer feeding. Runaway can mean super Eddington states that last longer than we expect, not as flashes but as sustained modes. It can mean low effective radiative efficiency because energy is trapped or carried inward. It can mean that the early universe favoured thick chaotic disks. It can also mean that feedback couples imperfectly, leaking out along paths that do not shut off the inflow. This is the conceptual meaning of something worse, and it is more unsettling than a single anomaly. It is the possibility that the early universe was not merely faster. It was less regulated, more nonlinear, and more willing to overshoot. The limits we quote may be averages, while the universe grows its giants in the tails. Now we handle alternatives carefully, because the title invites them, and because science is obligated to test its categories. Could TON 618 be something other than a standard black hole? Exotic compact objects are proposed in theory, from gravitar stars to boson stars to other horizonless states. They are attempts to resolve singularities or modify the endpoint of collapse. Most of those ideas are unnecessary to explain quasar phenomenology, and that is an important restraint. Accretion disks, winds, and jets arise from gravity plus plasma physics, and they do not require exotic interiors. Many alternative objects would still need to mimic the same external spacetime to match observations, especially at radii where the disk emits most strongly. The strongest reason scientists keep testing assumptions is not sensationalism. It is that the inference chain includes calibrations, and calibrations can drift at the extreme end. Broadline scaling relations are empirical, and the farthest, brightest quasars may not behave like the local sample. If the broadline region geometry changes, the virial factor changes with it. Accretion physics also includes uncertain microphysics, even when the big picture is clear. Magnetic field topology, radiation transport, and disk thickness change efficiencies and spectra. Small changes in these ingredients can shift inferred masses and growth histories. When we argue about early growth, we're often arguing about how these ingredients behaved under primordial conditions. Cosmological parameters also enter quietly through distance and luminosity, and they sit in the background of every energy estimate. A change in assumed cosmology changes absolute luminosity and therefore bolometric corrections. The effect is not enough to erase the problem, but it is part of honest accounting. Precision cosmology reduces the wiggle room, and that makes the remaining gap more meaningful. So the careful position is this, and it is more interesting than certainty. The black hole interpretation is the simplest consistent explanation for what we see. The real uncertainty is not whether gravity works. The uncertainty is how the early universe delivered fuel and how long it kept delivering. The engine is plausible, but the supply chain is the mystery. That returns us to the central question, and it lands with wait now. What is TON 618 really? It is a compact engine inferred from light, and it is a feedback machine that reshapes its environment. It is also a timestamp from deep time that arrives as photons now. The object is distant, but the evidence is present because light collapses distance into information. The opening hook becomes literal again, and the visuals can afford to slow down. 10 billion years ago, something violent happened around a monster. The evidence is arriving here now as light. Not a warning, not a prophecy, a message already written into the sky, then carried across an expanding universe. Now we address the threat line directly, because the story has earned it, and because clarity matters. What exactly is coming is not the object. Nothing about TON 618 is travelling toward us through space like a predator. The quasar is not migrating across the cosmos to find us. What is coming is radiation that has been in transit since the universe was young. It is photons, and possibly neutrinos and gravitational waves from associated events, stretched by expansion into longer wavelengths. The light arrives redder than it began, and fainter per unit area, but still legible to our instruments. Can it harm us? At this distance, no, and the reason is geometry as much as physics. By the time the light reaches Earth, it is a faint flux spread over a sphere billions of light years wide. It is information, not impact. The danger is not in the energy that arrives, but in what the energy implies. The unsettling truth behind coming is therefore psychological and scientific, and it sits in the gap between model and origin. The light carries proof that the early universe could build engines beyond our tidy timelines. It suggests that our limits are local approximations, not cosmic guarantees. It hints that the universe can grow giants while we're still writing the rules. This is the climax beat that points into the finale, and it is a fork in interpretation rather than a jump scare. If TON 618 is a standard black hole, then the worst thing is our incomplete story of growth. If it is not standard, then the worst thing is that our most trusted category may be only a label for ignorance. Either answer forces revision, and revision is the real pressure. Either way, the message is the same, and it is spoken in the language of horizons. The universe can assemble extremes and then hide their cause behind causality. We are left reading the glow around the darkness and calling it understanding. The glow is real, the understanding is partial, and the darkness remains an instruction to keep looking. In the final chapter, we step back from the engine room and ask what the message forces us to revise. We separate fear from physics, and we decide what certainty we are willing to lose. Then we ask the last question that TON 618 keeps asking us: how many more mouths of space opened early, fed fast, and vanished into history? We asked what is coming, and we pictured a monster crossing space toward us, like a predator on a straight path. That picture is wrong, and the correction is the real ending, because the universe does not behave like a fixed stage. TON 618 is not on a collision course with the Milky Way, and it is not even meaningfully headed anywhere in the everyday sense. The universe expands, and expansion changes what distance even means, because the ruler itself stretches while light is in flight. In astronomy, a quoted distance can be proper distance, comoving distance, or light travel distance, and each answers a different question. They agree nearby, where expansion is gentle over the travel time, and diverge hard at high redshift. Comoving distance tracks positions in the expanding grid, as if galaxies were pinned to cosmic coordinates that scale with the universe. Proper distance is the physical separation at a given cosmic time, the instantaneous gap you would measure with an imaginary chain. Light travel distance is the simplest to picture, because it is time turned into length using the speed of light. Yet even that can mislead, because the photon did not traverse a static corridor, space expanded beneath it. TON 618 sits at a high redshift, so the light left when the universe was much smaller and denser. The proper distance then was far less than it is now, which is why how far depends on when you ask. As space expands, most distant galaxies recede even if they are not moving through space locally, and that distinction matters. Recession is built into the metric, not into a rocket engine, and the equations of cosmology treat it as geometry. In the standard picture, galaxies are mostly at rest in their local neighbourhoods, while the scale factor grows between them. That growth turns into a redshift because each wave crest is stretched as the universe stretches. So when a catalogue says a quasar is moving away, it often means its redshift is high and its proper distance is increasing. That is not a trajectory aimed at us, and it is not a chase that can be won. Even peculiar velocities are small compared to cosmological recession at these scales, which is why local drift cannot reverse the trend. Local motions ride on top of expansion, and expansion dominates the long game, especially beyond galaxy clusters. There is a historical reason this still feels counterintuitive, because our instincts were trained on Newtonian space. Only in the 20th century did general relativity make room for a dynamic metric, and only later did Hubble's observations make expansion unavoidable. The phrase moving toward us has a narrow technical meaning, and it can be easy to misuse in popular retellings. It can mean a blue-shifted component in a spectrum, or a change in inferred proper distance, or a jet oriented along our line of sight. A wind can move toward us while the host galaxy recedes, because gas can be launched in many directions. A jet can point toward us while the quasar as a whole is carried away by expansion, and the two facts can coexist without contradiction. Redshift is not just speed, and it is not just distance, even though both can contribute in nearby space. It is a timestamp because it encodes how much the universe stretched since emission, and that stretch is a clock. When we say Z, we're compressing a story into a single symbol: how long the light travelled, how the scale factor changed, and how the intervening universe evolved. It is why a spectrum can feel like a message in a bottle, sealed in an earlier epoch. That is why the chase story fails, even if it is emotionally satisfying and easy to animate. TON 618 is not approaching to swallow us, because the space between us is not a fixed stage, and the distance is not a simple arrow. What is approaching is not matter. What is approaching is information, and it has been approaching since long before Earth formed, crossing an expanding cosmos that kept rewriting the meaning of between. The incoming signal is photons across the spectrum stretched by expansion and filtered by intervening gas along the line of sight. The message is faint, but it is structured, and the structure is where the science lives. Visually, imagine the quasar as a pinprick in a deep field image, surrounded by darkness that is not empty but thinly populated. Then imagine that pinprick unspooling into a spectrum, a barcode of bright peaks and carved-out troughs. We receive radio, infrared, optical, ultraviolet shifted into infrared, and sometimes X-ray hints through absorption and instrument limits. Each band samples a different radius of the engine, as if we are listening to different instruments in the same orchestra. Radio can trace jets and lobes, where magnetic fields guide relativistic particles into long, faint structures. Infrared can carry the heat signature of dust, re-radiating absorbed ultraviolet light like embers hidden behind smoke. Optical and ultraviolet, once corrected for redshift, are where the accretion disk announces itself most clearly. X-rays, when we can catch them, probe the hottest regions near the inner disk and corona, where electrons scatter photons to higher energies. The continuum tells us about the disk temperature profile, and the slope carries dust and geometry, not just raw power. The spectrum is a layered map of where energy was released and where it was reprocessed before escaping. In the simplest disk models, temperature rises inward, so different wavelengths correspond to different annuli of the disk. That is plain language for a sophisticated point. Colour is radius, and radius is gravity. The emission lines are the forensic record, and they are more than decoration on top of a smooth glow. Their widths encode velocities, and their ratios encode ionization and chemical enrichment, which together reveal both motion and composition. Broad lines imply gas moving thousands of kilometers per second in the deep potential, close enough to feel the black hole's grip. That is why the virial mass inference exists at all, because gravity writes itself into the Doppler-broadened profiles. When a line is wide, it is telling us that many parcels of gas are moving at many speeds along our line of sight. When it is asymmetric, it can hint at winds, obscuration, or a geometry that is not a simple spherical cloud. We already admitted the caveats in the weighing chapter, and they remain essential to intellectual honesty. The radius-luminosity relation can drift, the geometry factor can shift, and winds can bias certain lines, especially if outflows dominate the profile. There is also the practical reality that we observe through instruments with finite resolution and sensitivity, and through a universe filled with absorbing systems. Some wavelengths are eaten by neutral hydrogen, and some are blurred by noise, which shapes what we can claim. Those caveats matter, but they do not erase the scale of the problem, and they do not turn an extreme into an ordinary case. Even generous uncertainties leave TON 618 in the extreme tail, where rarity becomes the point rather than an inconvenience. Variability adds another constraint, and it is one of the most physically intuitive ones once you sit with it. A source that changes on short timescales must be compact, because causality limits how fast a large region can coordinate. If brightness doubles in days, the emitting region cannot be light years across, because a light year cannot hear a change in a day. That simple rule, nothing outruns light, turns flicker into a measuring tape. The flicker is not decoration. It is a clock, slowed by redshift and gravity, yet still pointing to a small engine, because the inner regions respond faster than the outskirts. In some quasars, different wavelengths vary with slight delays, as if a flash in the centre echoes outward through the disk. Those lags can be used to infer sizes, and they reinforce the picture of a compact, stratified structure. Polarization and absorption features add more layers, and they are easy to overlook because they are subtle. They reveal scattering geometries, intervening clouds, and outflows that reshape the line profiles, sometimes imprinting narrow absorption notches on broad emission. Polarization can tell us whether we see the central engine directly or mostly through scattered light, which matters for orientation. Absorption systems can also serve as mile markers, sampling the intergalactic medium the photons crossed on their long trip. So the broadcast is not a single number like mass or luminosity, and it is not a headline that fits on a graph. It is a packet of correlated clues, and the clues converge on an ancient accretion system that was already mature when the universe was young. This is where the twist lands, and it changes the emotional temperature of the story. The threat is not physical impact, because the flux that reaches Earth is harmlessly diluted, and distance is a protective ocean. At this distance, even a quasar cannot burn us, no matter how luminous the central engine once was. Energy spreads over a sphere billions of light years wide, and what arrives is a whisper, measured in sparse photons and careful statistics. Even if TON 618 radiated near the maximum allowed by its mass, the inverse square law still wins at cosmological scales. The night sky would be unlivable if distant quasars could scorch us, and the fact that it is not is a quiet reassurance. The worst thing is what the whisper says about the early universe, because it is a statement about capability. It says the universe could build monsters faster than our neat timelines allowed, and it did so under conditions we are still trying to reconstruct. Chapter 1 framed the core tension, and it remains the backbone of the mystery. Eddington limited growth gives an exponential clock, and the clock seems too slow for a tens of billions mass so early, unless something bends the rules. The Eddington limit is often summarized as a brightness cap, but it is really a balance between gravity and radiation pressure. If light pushes too hard on infalling gas, it can halt accretion, which turns luminosity into a governor on growth. We tried the standard escape routes, because science begins with the most conservative explanations. We asked if the mass is inflated by calibration drift, orientation, or line contamination, and we asked whether our assumptions smuggle in a bias. We asked if lensing secretly magnified the brightness, or if beaming made the source look stronger than it is, like a flashlight aimed at us. The checks do not give an easy exit, and the remaining room is not large enough to relax the tension. So we face the uncomfortable answer, and the discomfort is productive because it forces new work. TON 618 implies unusually massive seeds, sustained super Eddington phases, dense early environments, or a combination that multiplies rather than adds. Massive seeds reduce the number of E-foldings needed, which is why they are so attractive in the arithmetic. Direct collapse seeds in the 10^5 to 10^6 solar mass range change the calculation immediately, because you start closer to the finish line. Historically, the seed question has been a debate between light remnants and heavy beginnings, and each has consequences. Stellar remnants are common but small, while direct collapse is rare but powerful, and TON 6-18 pushes attention toward the rare track. But direct collapse needs special conditions, and special here is technical, not poetic. Molecular cooling must be suppressed, fragmentation must be avoided, and inflow must stay coherent under radiation, so the gas collapses as one rather than forming many stars. That suppression can require intense ultraviolet backgrounds that dissociate molecular hydrogen, or dynamical conditions that keep gas hot and stable against breaking apart. It is a narrow corridor in parameter space, which raises the question of how often nature finds it. Super Eddington growth changes the clock instead, and it does so by changing how radiation escapes. Thick disks can trap radiation, funnel light outward, and keep swallowing while appearing only modestly over the limit, because photons can be advected inward. In plain terms, the black hole can eat faster than it shines, at least for a while, because the light gets stuck in the flow. That does not violate physics, it exploits geometry and opacity, and it turns the accretion disk into a complicated machine. Yet Super Eddington cannot be a brief accident if the final mass is truly enormous, and that is where the pressure returns. It must recur or persist or be paired with heavy seeding, and each option demands an environment that keeps feeding the engine. Dense early environments supply the fuel, and they also supply the disturbances that drive gas inward. High redshift halos are compact, merger rates are higher, and filaments can deliver cold gas continuously, like rivers that do not dry up. In simulations, those filaments are not artistic flourishes, but gravitational highways, channeling baryons into the deepest potential wells. If a black hole sits at a privileged node, it can be fed repeatedly before feedback fully reorganizes the host. That is why the JWST chapter mattered, because it reframed the early universe as busy rather than sparse. A crowded early universe means more trials, more rare nodes, and more chances for runaway feeding, even if most galaxies remain modest. TON 6-18 then becomes less like a solitary glitch, and more like a boundary marker, placed at the edge of what our models comfortably produce. It marks where our subgrid recipes and feedback assumptions may fail, because the extremes expose every shortcut. This is where the investigative tone sharpens, because the constraints stack rather than cancel, and the escape hatches narrow. Every fix on one scale pushes stress onto another scale, and the system refuses to be solved with a single tweak. If seeds are heavy, we must explain how often the conditions occur, and whether they can happen early enough. If accretion is extreme, we must explain why feedback did not shut it down, or why the shutdown was delayed until after the growth was done. If environments are unusually dense, we must explain how structure formed so efficiently from the CMB-level perturbations, which started as tiny contrasts. The tail of the distribution becomes the story, because TON 6-18 lives in the tail by definition. The synthesis is not that our models are useless, and it is not that cosmology is broken. The synthesis is that our models were tuned to typical growth, and TON 6-18 interrogates the extremes, where rare pathways dominate outcomes. Structure formation is hierarchical, but hierarchy can still produce rare fast tracks, like a few trees that outgrow the forest. A privileged node can be fed by multiple filaments and repeated mergers, and the timing can align in a way that is statistically unlikely yet real. Feedback is real, but feedback is not always a break, and that nuance matters for narration and for code. It can vent along low-density channels, leaving the equatorial inflow line partly intact, so the system self-regulates unevenly rather than uniformly. Galaxy growth and black hole growth are coupled through shared gas, and that coupling can be tight when the system is young. If early galaxies assemble quickly, early black holes can be overfed before regulation stabilizes, and the later calm can hide the early sprint. That coupling reshapes the broader cosmological arc, because quasars do not merely sit in the universe, they modify it. Quasars ionize the intergalactic medium, enrich halos with metals, and alter cooling for later generations, which changes what galaxies can become. Rionization is often described as a phase change in the cosmic fog, and bright sources are the heaters. A quasar like TON 6-18 is a lighthouse in that era, and even if it is rare, it signals what the most extreme sights were capable of doing. So TON 6-18 is not just an object, and it is not just a record holder in a catalogue. It is a constraint on Rionization-era environments, on early metal production, and on how fast galaxies can organize when gravity and gas cooperate. Simulations now face a specific demand, and it is more stringent than matching averages. They must reproduce not only average luminosity functions, but the heavy tail of rare quasars without cheating the physics and without hiding the problem in resolution limits. That means resolving inflow, turbulence, and angular momentum transport, while modelling radiation transport and multi-phase feedback, which is notoriously difficult. The worst uncertainties live exactly there, in the messy interface between small-scale plasma and large-scale structure. It also means being honest about what we infer from light, because inference is translation across a gap we cannot cross directly. Our mass estimates are translations, and translations can fail at the edge of their dictionary, especially when we extrapolate beyond calibrated regimes. But even if the number shifts, the existence of a bright quasar at that epoch remains, and that is the immovable fact. Something was converting gravity into light at enormous rates, and the universe allowed it to happen early. So what is TON 6-18 really, when we strip away the chase story and keep the evidence? It is an ancient engine whose light encodes a growth history we did not expect to be possible, and it forces us to widen the menu of early pathways. And what exactly is coming toward us right now, across the stretched fabric of space? It is the delayed evidence that the early universe could run away, and that runaway episodes may be woven into the origin of later cosmic order. The menace is epistemic, not apocalyptic, and that distinction is the chapter's core. The incoming force is a rewrite of our origin story, because it changes what we think the universe can do quickly, before it settles into the slower rhythms we recognize. We like a universe that grows gradually, because gradual growth feels predictable and narratively tidy. TON 6-18 suggests the universe can sprint, overshoot and stabilize later, which is a more unsettling and more interesting kind of order. That possibility changes how we interpret everything else, because it changes our priors about what too early means. It changes how we read JWST's bright early galaxies, and how we search for hidden, dust-buried growth that optical surveys can miss. It changes what we expect from the first billion years, and it changes what we consider plausible in a simulation. It suggests that the first chapters were not quiet setup but violent assembly with extreme outliers, and those outliers may have downstream consequences. Now we return to the title, Provocation, and resolve it carefully, because language can mislead as easily as it can guide. TON 6-18 is almost certainly a black hole in the practical observational sense, meaning it behaves like one and fits the best-tested framework. But the phrase "not a black hole" points to a deeper truth, and it is a truth about labels. The label hides the mechanism, and the mechanism is what breaks our timelines, because growth is not a noun, it is a process. If the engine is standard, then the worst thing is that our growth channels are incomplete, and we have underestimated the efficiency of early feeding. If the engine is exotic, then the worst thing is deeper, because it would imply new physics or new regimes. Either way, the horizon keeps its secret, and that secrecy is part of the drama. We cannot see inside, and we infer the core from the glow that fails to cross the boundary, which is both a limitation and a powerful constraint. So the final answer is not fear of being eaten. The final answer is that time is the threat, because time delivers evidence we cannot unlearn, and the evidence arrives on a schedule we do not control. The night sky is an archive, and it is more literal than the metaphor suggests. Every point of light is a delayed event, arriving after travelling through an expanding universe, and every spectrum is a dated document. We do not look out into space and see the present, even when the stars feel immediate and familiar. We look back into history and watch the universe become itself, one photon packet at a time, with gaps and distortions that we learn to correct. Visually, the sky can dissolve into layers, like transparent sheets labelled with different epochs, each one farther and older. In that layered view, TON 6-18 sits on a distant sheet, shining from an era when galaxies were still assembling their basic shapes. TON 6-18 is a reminder that the most extreme chapters happened long before Earth existed, and long before the sun condensed from its own cloud. We are only now reading the first lines of that violence because the light had to cross time to reach us. And the message is already written, which is why it feels so strange and so final. It is not a warning sent to us, and it is not a prophecy about our future, because the event is long finished in its own frame. It is a record of what the universe has already done, and that record expands our sense of what is possible. If it built one monster that early, it can build others, and it can do it again, given the right initial conditions. So the coming is not a quasar crossing the void, and it is not a black hole drifting toward our doorstep. The coming is understanding crossing time, and it arrives whether we are ready or not, because photons do not care about our comfort. We end where we began, with light as evidence and with a quiet reversal of the original fear. 10 billion years ago, something violent happened around a monster, and the universe kept the receipt in the form of stretched, reddened waves. The evidence is arriving here, now, as light, measured, calibrated, and interpreted by minds that evolved on a small planet. Not a warning, not a prophecy, a message already written into the sky and delivered by time itself. We began with a simple idea, that the night sky is not a place but a delivery system, and TON 618 is a message arriving late. Its photons left when the universe was young, stretched from fierce ultraviolet into patient infrared, carrying brightness, line fingerprints, and timing cues across 10.4 billion years. We learned that we never see the black hole itself, we see the accretion engine around it, disk, corona, winds, jets, turning gravity into light with an efficiency stars cannot match. We traced how a star-like dot became a lighthouse once spectroscopy pinned its redshift, and how variability and emission lines proved the source must be compact, violent, and extraordinarily energetic. Then came the uncomfortable accounting, where broad line widths and radius, luminosity scaling relations translate Doppler-smeared gas into a mass estimate, and that estimate lands again and again in the tens of billions of suns. We also face the fine print, orientation factors, wind contamination, bolometric corrections, and the honor scatter that can move the number by a factor of 2 or 3. Yet even when you grant every caveat, TON 618 remains an extreme tail object, and its Eddington-level glow implies a central gravity well that is hard to shrink away with calibration alone. That is where the growth problem bites, because standard seeds and standard feeding rates struggle to reach this size before the universe's clock runs out. We walked through the proposed loopholes, heavy seeds from direct collapse, brief but repeated super Eddington episodes hidden inside thick disks, merger-rich nodes in the early cosmic web, or efficiencies and spins that change the pace of growth. JWST widened the stage, showing a first billion years that looks less like a quiet prologue, and more like a crowded menagerie, where luminous galaxies and candidate AGN appear earlier than our neat timelines prefer. And when we finally stepped into the engine room, we saw why the word black hole can mislead, because the real actor is the whole-coupled system of space-time, plasma, radiation, and feedback that can overfeed, self-regulate, and reshape its surroundings. So what is TON 618 really? And what is the something that is coming toward us right now? TON 618 is still a black hole in the strict sense, but it is also something worse for our certainty. A regime, a growth pathway, a cosmic loophole made visible. And what is coming is not the monster, it is the evidence. The light reaching us now is harmless in power, yet it is dangerous in meaning, because it suggests the early universe could build monsters faster than our rules allow. If TON 618 exists this early, then the cosmos is not only vast, it is capable of runaway extremes, and our timelines are not laws, just drafts waiting to be revised. When new spectra arrive and the next surveys deepen the first billion years, watch the